The night sky is not a quiet, empty place. It is constantly bombarding our planet with invisible bullets from deep space. These are cosmic rays, and the most powerful among them are the universe's ultimate mystery particles. We call them ultra-high energy cosmic rays, and their power is almost incomprehensible. A single one carries the energy of a Major League Baseball, but packed into a subatomic speck traveling at almost the speed of light. By the end of this journey, you will understand the 50 specific cosmic bullets that have left the world's top physicists completely stumped. Scientists have detected about 50 of these events, and each one shatters our models of physics. Where do they come from, and how can nature possibly accelerate a particle to such impossible extremes? What does it feel like to stand at the very edge of human knowledge, staring into a cosmic void? On October 15, 1991, a single speck of matter from beyond our galaxy tore through the atmosphere over Utah. It was not a star, not a comet, but a lone proton, a building block of an atom. The fly's eye cosmic ray detector, a sprawling array of mirrors and sensors, caught its spectacular death. In a flash of light, this one particle released an energy so immense, it forced scientists to invent a new nickname on the spot. They called it the "Oh my God" particle. The name was not an exaggeration. Its energy was measured at about 320 exa-electron volts. To make sense of that number, imagine a baseball, a simple 5-ounce sphere. Now imagine it hurled by a professional pitcher at 60 miles per hour. All the kinetic energy in that fastball was packed into a single, invisible proton smaller than an atom. It was traveling at 0.9999999999996 of the speed of light. In human terms, if a photon of light and this proton raced across the galaxy, the proton would lose by less than the width of a human hair. This detection did not just break a record. It shattered the entire rulebook. Every known object in the universe, from supermassive black holes to colliding galaxies, was suddenly called into question. None of them, according to our best physics, should be able to launch a particle with such ferocious power. The "Oh my God" particle was not just a discovery. It was a message written in the raw energy of the cosmos, and it said our understanding of the universe was profoundly, thrillingly incomplete. That single proton carried a paradox within its impossible speed. According to everything we know, it should not have been able to reach us at all. This is because of a cosmic speed limit for particles, a rule written into the fabric of space itself, known as the Greisen-Zatsepin-Kuzmin limit. To understand it, picture the universe not as a perfect vacuum, but as a faint, ghostly sea of light. This is the cosmic microwave background, the cooled remnant of the Big Bang's first flash, filling every cubic inch of space. For a proton traveling at nearly the speed of light, this faint background glow is not peaceful. It becomes a thick fog of high-energy radiation. The theory states that any ultra-high energy cosmic ray trying to cross intergalactic space will inevitably smash into these photons. Each collision is a brutal robbery, stripping the proton of its precious energy bit by bit. Over distances of hundreds of millions of light years, this process should drain them completely. The Greisen-Zatsepin-Kuzmin limit is the maximum energy a proton can possibly have when it finally reaches Earth from a distant galaxy. The "Oh my God" particle blasted straight through that limit. It arrived with an energy that, by all rights, should have been stolen from it eons ago. This presents scientists with only two unsettling possibilities. Either our understanding of particle physics across vast distances is fundamentally wrong, or this proton did not come from very far away. To survive its journey, it must have originated somewhere within our own cosmic neighborhood, within a radius of about 160 million light years. That sounds immense, but on the scale of the observable universe, it is practically next door. So the hunt began. astronomers turned their most powerful telescopes toward the patch of sky where the particle originated, searching for a cosmic monster capable of such an act. They looked for the usual suspects, colossal engines like active galactic nuclei, where supermassive black holes devour matter and spew out jets of radiation. They scanned for supernova remnants or colliding galaxies. The result was a profound silence. That direction of space within that critical distance showed nothing. No titanic explosion, no swirling disk of doom, no celestial beacon powerful enough to be the culprit. The most energetic particle ever seen seemed to have come from nowhere. This is the heart of the Defiance. We caught the bullet, we measured its incredible power, and we traced its path back, only to find an empty gun. 2 years later, the silence was broken by another scream. In 1993, the same fly's eye detector in Utah captured a second ultra-high energy event. This cosmic ray carried an energy just above 200 exaelectron volts. While slightly less powerful than its legendary predecessor, its significance was monumental. It proved beyond any doubt that the "oh my God" particle was not a mistake. It was not a glitch in the machine or a fleeting anomaly in the data. The universe was doing this on purpose. Here was a second bullet fired from the same cosmic gun, confirming that our models of physics were facing a systematic challenge. These were not impossibilities, they were regular occurrences. The detection sent a clear message to the scientific community. The energy frontier was real and it was populated. Physicists could no longer dismiss the first event as a once-in-a-lifetime fluke. They now had to confront a universe capable of routinely accelerating particles to energies they had once labeled impossible. This shifted the entire conversation from whether such things could happen to how they were happening. The debate then turned to origins. Researchers meticulously analyzed the incoming direction of this second particle, comparing its path to that of the "oh my God" particle. Was there a correlation, a hint that both might have been launched from the same catastrophic event or the same mysterious object in the void? Some studies suggested a tantalizing, though not conclusive, alignment in their trajectories. This faint hint pointed toward a potential point source, a single cosmic engine powerful enough to fire multiple shots across the eons. Yet, just like before, when telescopes scanned that region, they found no obvious culprit. So the mystery deepened. Not only did these particles defy the laws of travel, they now seemed to be emerging from shadows, from places we could not see or comprehend. The second fly's eye event transformed a shocking outlier into a pattern, and a pattern demands an explanation. The silence from the cosmos was not an answer, it was a challenge. To meet it, scientists needed a sharper eye, a finer instrument to dissect these fleeting ghosts of energy. The original fly's eye evolved into something far more powerful, the high-resolution fly's eye experiment, or high-res. Its mission was simple: capture the uncatchable with unprecedented clarity, and it did not have to wait long. One of its early detections, a cosmic ray with an energy well over 200 exaelectron volts, became a landmark. It was not the most powerful ever seen, but it was the most precisely understood. High-res achieved this through a beautiful and indirect method, watching the sky itself glow. When an ultra-high energy cosmic ray slams into the atmosphere, it does not just vanish. It creates a cascade of secondary particles, an avalanche of matter and antimatter streaking toward the ground. This avalanche excites nitrogen molecules in the air, causing them to fluoresce, to emit a faint ultraviolet light. The high-res detectors were essentially giant, sensitive mirrors designed to catch this specific ghostly glow. By tracking the progression of this ultraviolet streak across the night sky, scientists could triangulate the cosmic ray's trajectory with far greater accuracy than before. They could also measure the total amount of light produced, which directly tells them the primary particle's original energy. This event was a masterclass in cosmic forensics. The improved data was a gift to theorists who were still reeling from the implications of the earlier detections. Now, instead of arguing over the basic reality of these impossible particles, they had a cleaner, sharper data point to anchor their models. The high-res detection helped shift the conversation from "is this happening" to "how is this happening?" It confirmed that the phenomenon was not only real, but it was also something we could study with increasing precision. Every new measurement was a tighter constraint, a narrower box into which any potential explanation must now fit. The mystery was not fading with better tools, it was coming into a much sharper, much more confounding focus. The clarity of high-res brought a new kind of frustration. Another of its captured events, a cosmic ray with energy soaring past 150 exaelectron volts, presented a perfect example. Scientists followed its ultraviolet trail back through the cosmos with meticulous care, a process called backtracking. They traced its incoming line across millions of light years, searching for a source. The expectation was to find a cosmic landmark, a brilliant beacon like a nearby active galaxy with a voracious black hole, a blazing quasar, or the fading afterglow of a cataclysmic gamma ray burst. The data led them to a specific patch of sky, and the world's most powerful telescopes swung into alignment. They looked and they saw nothing, not just no obvious source, but a profound emptiness. No major galaxies, no violent stellar nurseries, just the quiet dark of the intergalactic void. It was as if a cannonball had been fired from the middle of an empty ocean. This is where the mystery twists. The problem may not be that the source is invisible, but that the map is crooked. The particles we are detecting, like protons, carry an electric charge. They are not neutral travelers, they are charged bullets, and our universe is threaded with invisible magnetic fields, not just within our own galaxy, but in the vast spaces between galaxies as well. These fields are incredibly weak, far weaker than a common refrigerator magnet, but they are woven across incomprehensible distances. As a charged proton races across the cosmos for 100 million years, even these faint magnetic fields gently tug on it, bending its path. This is called magnetic deflection. Imagine trying to trace the origin of a single, specific raindrop back to the exact cloud it fell from, while a constant, shifting wind has been blowing it sideways the entire journey. The task becomes nearly impossible. The direction we see it coming from is not where it began. It is merely the last bend in a long, winding road. That seemingly empty patch of sky might be a cosmic mirage. The true source, the cosmic accelerator, could be hiding somewhere completely different, its signals scrambled by the magnetic fog of intergalactic space. This deflection adds a maddening layer of complexity. We are not just looking for a needle in a haystack, we are trying to find the haystack while the needle has been moving in the dark for eons. This magnetic fog left scientists with a ghostly trail, but the pursuit was far from over. On the other side of the world, a different kind of hunter was listening to the sky. In the mountains of Japan, the Akino giant air shower array, known as Agasa, spread across a sprawling 1 square kilometer. Its method was not to watch for faint ultraviolet light, but to feel the impact. Instead of mirrors, it was a grid of over 100 concrete detectors filled with scintillator plates waiting on the ground. When the cascade of secondary particles from a cosmic ray shower rained down, these plates would flash with light, a direct and violent footprint of the primary particle's energy. Agasa listened for the thunder, not the lightning, and what it heard was a roar that challenged everything. One of its detected events reported an ultra-high energy cosmic ray with a staggering energy that soared far above the theoretical Greisen-Zatsepin-Kuzmin limit. This was not a quiet whisper from the edge, it was a shout from beyond the boundary. But the real controversy was not about one single particle, it was about a pattern. Over its years of operation, Agasa reported seeing more of these super-high energy events than anyone had predicted. Its data suggested a higher flux, a greater number of these impossible particles raining down on Earth than the Greisen-Zatsepin-Kuzmin theory allowed. If the limit was a true wall imposed by the universe, then Agassiz results showed particles regularly scaling that wall. This created a direct and public tension with the high-res experiment. The two premier detectors, using fundamentally different techniques, seemed to be telling two different stories about the same sky. One saw a universe that mostly obeyed the rules, with only rare, shocking exceptions. The other saw a universe where the rules were being broken all the time. The debate was not about which machine was wrong, but about what the universe was truly doing. Was the Greisen-Zatsepin-Kuzmin limit softer than we thought? Were we misunderstanding how protons lose energy on their epic journeys? Or was there an entirely new type of particle, something neutral like a photon or a neutrino that could travel unaffected by the cosmic microwave background, masquerading as these ultra-high energy events? The Agassiz controversy forced physicists to question the very nature of the bullets themselves. It was no longer just a hunt for sources in empty space. It became a fundamental interrogation of our cosmic inventory. The stage was set for a showdown, and it would require a detector of unprecedented scale to settle the score. The debate over the flux was just the beginning of Agassiz challenge. The array's data held an even more tantalizing clue, one that seemed to point a trembling finger directly at the sky. Scientists noticed something peculiar when they plotted the arrival directions of its most energetic events. A handful of these cosmic rays, instead of being scattered randomly across the heavens, appeared to arrive in tight little groups, clustered together in the same small patches of sky. This was the clustering puzzle. If these particles were truly coming from the empty voids between galaxies, as their deflected paths suggested, their arrival should be a perfect random sprinkle. Finding a cluster was like finding several bullets fired across millions of years, all landing in the same tiny target. It hinted at a single, monstrous engine out there in the dark, not just exploding once, but firing repeatedly over cosmic time. The statistical argument for this was a delicate dance of probability. Researchers calculated the odds that such a tight grouping could happen by pure chance, given the number of events Agassiz had seen. For one particular triplet of ultra-high energy events, the odds seemed surprisingly low. This was not proof, but it was a compelling whisper, a suggestion that we might finally be looking at the faint, blurred signature of a specific source. A cosmic lighthouse, perhaps, whose beam occasionally swept across our planet. The argument against clustering was equally powerful. With so few events to study, statistics can play cruel tricks. A random distribution, by its very nature, can sometimes look clustered. It is the celestial equivalent of rolling a die and getting 2 sixes in a row. It feels meaningful, but it can still be chance. Furthermore, the relentless magnetic deflection meant that even particles born in the same catastrophic event could be bent along wildly different paths by the time they reached us, arriving from seemingly different directions. So, were these clusters a real signal or just a statistical mirage? This question became a driving force in cosmic ray science. To answer it, scientists needed more data, far more than Agassiz or high-res could provide alone. They needed an observatory so vast it could catch these ultra-rare events in meaningful numbers, an instrument with the statistical power to distinguish a true pattern from a cosmic coincidence. This urgent need for a definitive answer is what finally gave birth to a giant, the Pierre Auger Observatory. The need for a definitive answer demanded a new kind of instrument, one built on a scale that matched the ambition of the questions. So they built a giant's eye on the high plains of Argentina. The Pierre Auger Observatory is not a single telescope, but an entire landscape transformed into a scientific instrument. It sprawls across 3,000 square kilometers, an area larger than some small countries, dotted with 1,600 separate detectors. Each one is a cylindrical tank filled with 12,000 liters of ultra-pure water, sitting silently under the vast southern sky. Their method is deceptively simple. When the secondary particle shower from an ultra-high energy cosmic ray rains down, it enters these tanks faster than the speed of light in water. This creates a faint blue flash of light called Cherenkov radiation, which sensitive photomultiplier tubes lining the tanks can capture. By timing the arrival of this flash across hundreds of tanks spread miles apart, the array can reconstruct the direction and energy of the primary cosmic ray with astonishing detail. But the Auger collaboration went further, adding a second, overlapping sense. Surrounding this giant array are 24 fluorescence telescopes positioned on the outskirts to peer inward. These watch for the same ultraviolet glow of excited nitrogen that the fly's eye experiments pioneered. This hybrid design is the observatory's genius. The ground array catches almost everything that falls within its borders, providing immense statistical power. The fluorescence telescopes offer a direct colorimetric measurement of the energy, a cross-check of unparalleled precision. Together, they see the same event in two completely different ways, eliminating doubt and refining the data to a razor's edge. One of its early flagship detections was a cosmic ray with an energy well over 200 exa-electron volts. The event was not remarkable for its raw power, which was now almost expected, but for the sheer volume of information it yielded. For the first time, scientists had not just a bullet's trajectory, but a full forensic report. They could see the detailed shape of the particle cascade, the distribution of its energy in the atmosphere, and could cross-reference the water tank timings with the ultraviolet light curve. This single event provided more constraints on theoretical models than a dozen of the older detections combined. It marked a profound shift in the field. We were no longer just collecting shocking anecdotes about the universe. With Auger, we began taking a systematic census of the impossible. The mystery was not solved, it was multiplied. Every precise measurement from this new giant was a new piece of a puzzle we are only beginning to assemble. The data from the Pierre Auger Observatory began to tell a new, more nuanced story. While it captured its own share of ultra-high energy monsters, its true power lay in the sheer number of events it recorded, painting a statistical portrait of the cosmos. What emerged from years of patient observation was a subtle but unmistakable pattern in the data, a cosmic cliff edge. The observatory detected a clear and steep drop in the number of cosmic ray events with energies above about 60 exa-electron volts. This was not a gentle decline, it was a sudden fall-off, a steepening in the spectrum that matched a prediction made decades earlier. It was the long-sought signature of the Greisen-Zatsepin-Kuzmin cutoff, the effect of the cosmic microwave background finally making its mark on the data. For the first time, we had strong, large-scale evidence that the rule was real. The faint glow of the Big Bang was indeed acting as a cosmic break, sapping the energy of the most powerful particles as they traveled across the universe. This finding was a major victory for the standard model of particle physics and cosmic ray propagation. It aligned beautifully with earlier hints from the high-res experiment, confirming that our basic understanding of how these particles lose energy over intergalactic distances was fundamentally correct. The universe, it seemed, was playing by the rules after all, but this confirmation created an even deeper paradox. If the Greisen-Zatsepin-Kuzmin cutoff is a real and effective barrier, then the few cosmic rays that smash through it, the ones with energies far above 60 exa-electron volts, become infinitely more perplexing. Their existence is not just surprising, it is defiant. They are the exceptions that prove the rule is being broken. Think of it like discovering a natural law that says no object can be thrown faster than 100 miles per hour. You observe millions of throws and see the distribution drop off exactly at that speed, confirming the law. But then, once every few years, you find a baseball that was somehow thrown at 200 miles per hour. The rule works perfectly until it doesn't. The Auger data solidified the cliff, making the few particles that sailed over it into profound outliers. These were not just slightly above the limit, they were soaring far beyond it, carrying energies that, according to the very rule the data now supported, should have been stripped away. So the questions sharpened from where do they come from to how do they survive. Either these particles are a different kind of traveler entirely, a neutral particle like a photon that ignores the cosmic microwave background, or they come from so incredibly close that they did not have time to be slowed down. A source within our own galactic neighborhood, a cosmic accelerator of unimaginable power, sitting practically in our backyard and remaining completely invisible to every telescope we have. The confirmation of the rule did not solve the mystery of the 50, it made their defiance even more brilliant and strange. While the Auger Observatory scanned the southern skies, a different watchtower kept vigil in the north. In the desert of Utah, the telescope array unfurled its own version of a giant's eye, a sprawling grid of over 500 scintillator detectors covering 700 square kilometers. Its purpose was complementary, to catch the same impossible bullets from the opposite half of the cosmos. One of its standout detections, a cosmic ray with an energy cresting 150 exaelectron volts, was a perfect northern counterpart to Auger's southern catalog. But the true power of having two giants awake in the world was not just in counting events, it was in comparing their maps. Scientists could now search for anisotropies, for imbalances in the direction these particles arrive from. If the universe's most powerful accelerators were clustered in specific regions, like a belt of cosmic volcanoes, then one hemisphere's sky might look significantly busier than the others. The data began to whisper a tantalizing hint. Both observatories independently reported a curious excess of ultra-high energy events from a broad region of the sky. For the telescope array, this was a patch in the constellation Ursa Major. For Auger, it was a zone toward the constellation Centaurus. These were not the tight clusters Agasa once suggested, but broader, hotter spots on the cosmic map. The fact that two different experiments, using different techniques on different continents, saw similar large-scale patterns was electrifying. It suggested we might finally be seeing a faint imprint of the universe's large-scale structure in the rain of cosmic rays, a hint that these particles are not coming from nowhere, but are tracing the hidden skeleton of galaxies and dark matter. Yet here lies the beautiful tension of modern science. While both giants saw anisotropies, the specific hotspots did not perfectly align, and the statistical significance of each was a delicate, debated number. Some researchers argued the telescope array's northern hotspot was particularly compelling, a persistent overabundance that refused to fade with more data. Others pointed out that Auger's southern excess, while real, could still be consistent with a chance fluctuation given the complex magnetic deflections the particles endure. This ongoing dialogue is not a failure, it is the sound of the mystery being squeezed from both sides. Every new event from Utah or Argentina adds another pixel to a picture we are still learning how to see. The debate itself proves we are asking the right questions, and that the answers, when they finally solidify, will be written across the entire sky. The northern sky holds a persistent whisper, a region where the map of the universe seems slightly brighter. For over a decade, the telescope array in Utah has been recording a curious excess of ultra-high energy cosmic rays arriving from a broad patch of sky near the constellation Ursa Major, the Great Bear. This is the so-called northern hotspot, a blurry but stubborn signal that refuses to fade away. Unlike a single, impossible bullet, this is a statistical anomaly, a gentle hill on an otherwise flat landscape suggesting that from this general direction, just a few more of these cosmic ghosts arrive than pure chance would allow. Its location is not in a complete void, but it does not point directly at any obvious, brilliant source either. It simply hangs there, a diffuse glow on the cosmic map, tantalizingly close to the supergalactic plane, the vast flattened structure where thousands of galaxies, including our own, are gathered. The excitement was immediate and profound. Could this finally be it, not the pinpoint of a single gun, but the smeared signature of a cosmic factory, a hidden accelerator of such power that its faint spray of particles was just now washing over Earth? For a moment, it felt like the first real clue, a crack in the mystery where light might finally get in. Skepticism, however, is the essential counterweight in science. The hotspot is broad, covering about a quarter of the northern sky. With so few total events, even a small random clustering can look significant. It is the astronomical version of seeing a face in the clouds. The pattern is clear, but is it meaningful? Critics argued that given the small number of detections and the immense magnetic scrambling these particles endure, such an excess could still be a cruel statistical fluke, a temporary mirage that would vanish as more data was collected. Yet the telescope array kept watching, and the hotspot did not vanish. With each passing year and each new ultra-high energy event that fell within its borders, the signal grew a little stronger, a little harder to dismiss as mere chance. This created a beautiful tension, a pendulum swing between hope and doubt. Here was a potential answer shimmering just out of reach, a promise that the universe was not merely firing random shots in the dark, but that its most powerful artillery might have a preferred target. But if this was a real source, why was its signal so blurred and diffuse? The answer, once again, points to the invisible hand of intergalactic magnetism, bending the paths of these charged particles over millions of years until their origin is not a point, but a faint, glowing smear across the stars. The hotspot offers a destination for our search, but it is a destination without a landmark, a neighborhood without an address, deepening the mystery even as it seems to solve it. That northern whisper is answered by a southern shout. Among the many ultra-high energy events captured by the Pierre Auger Observatory, one stands out for pointing a trembling finger at a known celestial monster. Its incoming trajectory traces a line back toward Centaurus A, one of the closest active galaxies to our own, a mere 12 million light-years away. This proximity makes it an irresistible suspect. Centaurus A is no quiet neighbor. It is a colossal radio galaxy, a chaotic engine powered by a supermassive black hole weighing tens of millions of times our Sun's mass. From its core, it blasts out twin jets of plasma at nearly the speed of light, which then inflate into gigantic, bubble-like lobes of radio emission that stretch far beyond the galaxy's visible stars. These lobes are immense natural particle accelerators, magnetic caverns where charged particles could theoretically be whipped to incredible speeds over vast distances. If you are looking for a cosmic factory capable of manufacturing ultra-high energy bullets, Centaurus A fits the profile perfectly. It is powerful, it is close, and its very structure suggests it is in the business of launching matter across the universe. The discovery of a cosmic ray seemingly coming from its direction felt for a moment like a breakthrough. Finally, a name to put to the mystery. Here was a potential culprit caught in the act. But this is where the conundrum tightens its grip. While the arrival direction is suggestive, it is not a smoking gun. The particle's path does not point with laser precision to the bright core of Centaurus A. Instead, it points roughly into the same broad patch of sky. This blurring is the work of those intergalactic magnetic fields, the same ones that scramble all our cosmic signals. For a charged proton traveling 12 million light-years, even the faintest magnetic tendrils will bend its path significantly. Scientists estimate the deflection could be anywhere from a few degrees to over 20 degrees by the time it reaches us. On the scale of the night sky, that is a massive margin of error. It is the difference between pointing directly at a single house on a distant street and pointing at the entire neighborhood that surrounds it. So while Centaurus A sits within the possible origin zone, so do countless other patches of empty space, unseen dwarf galaxies, or entirely different objects hiding in the magnetic fog. Furthermore, not every ultra-high energy event from that general direction lines up with Centaurus A. Other cosmic rays have been recorded from the Centaurus region whose backtracked paths, when corrected for likely magnetic bending, miss the galaxy entirely. This is the heart of the conundrum. We have a prime suspect with motive and opportunity standing right in the cosmic lineup, yet the evidence is too smudged by the universe itself to secure a conviction. Centaurus remains the most compelling nearby candidate we have, a tantalizing maybe that keeps astronomers staring intently at its violent, jet-spewing core, wondering if we are finally seeing the echo of its power in a single, impossible speck of matter that crossed the void to find us. While Centaurus remains a prime suspect, the cosmic detective work extends far beyond our immediate neighborhood. Another of the 50, a cosmic ray with energy soaring past 100 exa-electron volts, presents a different kind of puzzle. Its arrival direction points roughly toward the Virgo cluster, a dense swarm of over 1,000 galaxies some 55 million light-years away. This is not a single suspect, but an entire metropolis of potential accelerators, a cosmic city where violent events are far more common than in the lonely voids of space. Within that bustling cluster lies a true giant, the galaxy M87. It is famous for two reasons. It houses one of the most massive black holes ever imaged, and it fires a spectacular jet of plasma thousands of light-years long directly from its core. This jet is a natural particle cannon, a focused beam of matter and energy that seems perfectly designed to launch the kind of bullet we detected. If you are searching for an engine capable of creating an ultra-high energy cosmic ray, M87's jet is a textbook candidate. Yet, the association is frustratingly vague. The cosmic ray did not point like an arrow to M87 itself. It came from the general direction of the entire Virgo cluster, a blur that encompasses hundreds of other galaxies, any of which could harbor hidden, violent processes. This is where the nature of the bullet itself becomes critical. Was it a proton or something heavier? The answer changes the entire investigation. A proton, being a single, lightweight hydrogen nucleus, carries a single positive charge. As it journeys through intergalactic magnetic fields, that charge makes it susceptible to deflection, but less so than a heavier nucleus. Imagine two objects thrown into a crosswind, a lightweight plastic bead and a heavy steel ball bearing. The wind will push the lightweight bead off course much more easily. In cosmic terms, a proton is that plastic bead. Its path gets bent, but not as severely as the path of an iron nucleus, which carries 26 times the charge and is far more massive. If the cosmic ray from Virgo was a proton, then its original trajectory was only moderately scrambled. That means its true origin is more likely to be closer to the direction we observed, tightening the search around specific objects like M87. But if it was a heavier nucleus like iron or silicon, then the magnetic fields could have whipped it around like a leaf in a hurricane, sending it on a wild, looping path that makes tracing its source nearly impossible. So the simple question, what is this thing made of, becomes the key to unlocking the map. The composition of these cosmic bullets is not just a detail, it is the cipher that can decode their origins, telling us if we are looking at a precise beacon or a cosmic mirage. So the question of composition is not a side note, it is the central clue. For decades, the assumption was that these cosmic bullets were lone protons, the simplest and most common building block in the universe. But what if some of them are not protons at all? What if they are entire atomic nuclei like iron or silicon, stripped of their electrons and hurled across the cosmos? This is the heavy nucleus mystery, and it changes everything about the hunt. Imagine the difference between firing a single, lightweight marble and firing a cannonball made of solid iron. Both can be devastating, but they behave utterly differently in flight. A proton with its single positive charge is nudged by cosmic magnetic fields. A heavy nucleus like iron carries 26 times the electric charge. To those same magnetic fields, it looks like a massive, bright target. the forces acting upon it are far stronger, whipping it around with much greater force over its million-year journey. This means a heavy nucleus cosmic ray could be bent so severely that its arrival direction becomes almost meaningless for finding its source. The beautiful, straight line we trace back into the sky might be a complete illusion, a path twisted into a pretzel by the magnetic fog of intergalactic space. The empty patches of sky we keep finding might not be empty at all. The true accelerator could be hiding in a completely different part of the cosmos, its signals scrambled beyond recognition. Yet, this heavy composition might also solve part of the energy puzzle. Some theoretical models suggest it could be easier for certain cosmic accelerators, like the turbulent shockwaves around colliding galaxies, to push a heavier, more complex nucleus to these extreme energies than a lone proton. It is a different kind of launch mechanism. Think of it like a sailboat versus a tanker. A proton is the sailboat, light and fast, catching the wind easily but also blown off course by every gust. A heavy nucleus is the tanker, massive and sluggish to start, but once a truly colossal force gets it moving, its immense momentum carries it forward with terrifying power, even as currents push it sideways. One of the 50 events adds critical weight to this possibility. Scientists scrutinized the atmospheric shower it created, the cascade of particles as it disintegrated in the air. The pattern of that cascade, how deep it penetrated before reaching its maximum number of particles, is a telltale fingerprint. A proton shower tends to develop higher in the atmosphere. A shower from a heavy nucleus, because it is like a tightly bound cluster of protons and neutrons, holds together a bit longer before exploding, creating its maximum cascade lower down. The profile of this particular event suggested it was not a proton. The data whispered it was something much heavier, perhaps an iron nucleus or something similar. This single piece of evidence transforms the unsolved equation. We are no longer just searching for a source in the void. We are now also trying to identify the bullet itself, and the answer dictates where we should even look. Is the mystery of the 50 a problem of invisible sources, or is it a problem of cosmic camouflage, where the particles themselves are master deceivers, wearing magnetic disguises that lead us endlessly astray? The search for a straight line through the magnetic fog led scientists to hunt for a different kind of messenger altogether. What if the most powerful cosmic bullets were not charged protons or heavy nuclei, but packets of pure light? We are talking about ultra-high energy photons, gamma rays with the staggering power of hundreds of electron volts. Finding one would be the ultimate cosmic clue. Unlike a proton, a photon has no electric charge. It is neutral. This means it ignores the universe's magnetic fields completely, traveling in a perfect, unwavering line from its birth to our detectors. If we could catch one of these photon phantoms, its arrival direction would be a flawless arrow, pointing with unerring precision straight back to the door of the accelerator that created it. No deflection, no scrambling, no guesswork. It would be a signed confession from the cosmos. The hunt for these ghostly lighthouses has been intense, spanning decades and involving the world's most sensitive gamma-ray observatories. Experiments like the High-Energy Stereoscopic System, or HESS in Namibia, and the Very Energetic Radiation Imaging Telescope Array System, or VERITS in Arizona, have scanned the skies for these telltale streaks of pure high-energy light. They have looked toward the usual suspects like Centaurus and the active galaxies in Virgo, and they have looked into the empty voids where other cosmic rays seem to originate. The result has been a profound and puzzling silence. Not a single conclusive ultra-high energy photon has ever been found. This absence is not for lack of trying. One particular analysis from the Pierre Auger Observatory placed a stringent upper limit. After years of data, they could state with confidence that fewer than 1.4% of the highest energy cosmic rays could possibly be photons. In the world of particle physics, an upper limit is a powerful statement. It tells you what is not there. This near-total absence of photons slams the door on a whole class of exotic theories. Some of the most speculative ideas for what could create these particles, like the decay of hypothetical super-heavy dark matter particles or the evaporation of primordial black holes, would be expected to produce a significant shower of these neutral photons alongside the charged particles. The fact that we see virtually none means those theories, while fascinating, are likely wrong, or at least not the primary source of our 50 cosmic bullets. So we are left with a new layer of the mystery. The universe is firing unimaginably powerful charged bullets at us, bullets whose paths are hopelessly scrambled. Yet it refuses to fire a single straight one, a clean signature that would solve the case overnight. This tells us that whatever cosmic engine is at work, it is not just powerful, it is also selective. It seems to specialize in accelerating matter, not pure light, or it operates in an environment so thick with radiation that any photons it does create are immediately absorbed before they can escape. The phantom photon remains just that, a ghost we cannot catch, and its absence is a clue that deepens the darkness around our 50 impossible events. The silence around phantom photons is echoed by another missing piece of the puzzle, a ghost within the ghost. To understand this, we must follow the chain of destruction. When an ultra-high energy cosmic ray, especially a proton, finally collides with a photon from the cosmic microwave background, it is not a quiet event. It is a catastrophic explosion on a subatomic scale. This collision, governed by Einstein's famous equation, creates a shower of new particles, including pions. And these pions, when they decay, produce a specific signature. They should generate ultra-high energy neutrinos. Neutrinos are the universe's ultimate ghosts, particles with almost no mass and no charge, barely interacting with anything. They can fly straight through planets as if they were not even there. So if our 50 cosmic bullets are indeed protons being shredded by the cosmic background light on their long journeys, then their death should be broadcasting a faint but detectable siren song of neutrinos across the universe. We should be able to point our most sensitive neutrino telescopes toward the general directions of these events and hear an echo. This leads us to cosmic ray 15, another member of the 50, with an energy well into the forbidden zone. Its arrival was recorded with precision, its path backtracked into a specific slice of the cosmos. The moment it was detected, a silent alert went out to the world's neutrino hunters. Deep under the ice at the South Pole, the Ice Cube Neutrino Observatory, a cubic kilometer of instrumented ice, listens for the extremely rare flashes of light created when a neutrino actually does interact. It is tuned to hear the whispers of these ghost particles. Scientists pointed Ice Cube's virtual ear toward the origin of cosmic ray 15, searching for a neutrino that arrived at roughly the same time, or even within a reasonable window afterward, a cosmic birth certificate from the same violent event. They found nothing, just empty, silent ice. This non-detection is not an isolated case. Across multiple ultra-high energy cosmic ray events, the expected chorus of high-energy neutrinos has simply failed to appear. The universe is firing the bullets, but it is not producing the shell casings we expect to find at the scene. This missing neutrino signal puts immense pressure on some of the most straightforward theoretical models. It suggests that maybe these protons are not interacting with the background radiation in the way we think they should. Perhaps they are not protons at all, but heavier nuclei whose interaction patterns are different. Or maybe, and this is the truly mind-bending possibility, they are not coming from far away. If these cosmic rays are born very, very close to our galaxy, they would not have traveled far enough through the sea of background photons to produce a significant number of pions and therefore the expected neutrinos. Their journey would be too short to leave the calling card we are listening for, so the quiet from the ice is another form of data, a profound absence that tells us our map of the cosmic battlefield is missing entire territories. We are left with the bullet, the empty sky it came from, and now the silence of the ghosts that should have accompanied it. The galactic plane is a highway of stars, dust, and familiar cosmic violence, but it is not supposed to be a source of the universe's ultimate bullets. This brings us to cosmic ray 16, an event that arrived not from some distant, empty void, but from a direction tracing a line frighteningly close to the crowded disk of our own Milky Way. Its detection sent a ripple of unease through the community because it challenges a foundational assumption that all ultra-high energy cosmic rays must come from beyond our galaxy. The reasoning has always been simple: our galaxy, for all its supernova explosions and swirling magnetic fields, simply does not contain an engine powerful enough. Think of it like a local cannon versus an intercontinental ballistic missile. The most violent events within the Milky Way, like the remnant of a supernova, can accelerate particles to incredible speeds, but they top out. Their reach has a ceiling, and that ceiling is far, far below the energy carried by cosmic ray 16 and its kin. The magnetic fields within our galaxy, while strong, are also tangled and chaotic, making it impossible for them to focus and accelerate a single particle to such an extreme over a short distance. So the detection of an ultra-high energy event from the galactic plane presents a stark either-or. The first possibility is the shocking one, that our understanding of galactic power sources is completely wrong. Is there a hidden monster lurking within the spiral arms, something we have overlooked? A hyper-energetic pulsar, a quiet black hole binary system undergoing a catastrophic merger, or some exotic object we have not yet even named. This would be a revolution in our backyard, a discovery that the most powerful particle accelerators in existence might not be in distant galaxies, but hidden in plain sight within the starry fog of our own. The second possibility is more conventional, but no less tricky. Perhaps cosmic ray 16 is indeed extragalactic, born in a distant galaxy or cluster, but its path to us happens to pass directly through the dense plane of the Milky Way. We are seeing a background source through the galactic disk. This is like trying to spot a specific house in a distant city while staring directly down a brightly lit, foggy street in your own town. The foreground clutter of stars, gas, and dust not only obscures the view, making it impossible to identify the true source with telescopes, but it also complicates the particle's journey. The Milky Way's own magnetic fields, much stronger than the faint intergalactic ones, would have exerted a powerful and unpredictable pull on the charged particle as it entered our galactic neighborhood. This would further scramble its final approach, making the task of backtracking its true origin a nightmare of calculations and guesswork. So cosmic ray 16 sits at a crossroads, a single data point pointing two ways. It either forces us to rewrite the book on what is possible inside a galaxy like ours, or it confirms that the universe's greatest mysteries can be perfectly hidden behind the most familiar scenery. This one event reminds us that the map of the impossible is not just drawn on the voids between galaxies, but may also be written in the starlight right in front of us. The most defiant of all refuse to even acknowledge the limit exists. Cosmic ray 17 was not just another high-energy event, it was a declaration of war against our understanding of physics. Detected with stunning clarity by the Pierre Auger Observatory, its energy measurement left no room for polite debate. It soared past 250 exaelectron volts, a number so far beyond the Greisen-Zatsepin-Kuzmin cutoff it seemed to mock the very concept. To grasp its power, think of the oh my god particle, that legendary cosmic fastball. Cosmic ray 17 was like catching a second fastball, but this one was fired from a cannon. Its energy was not just above the theoretical wall, it was in another stratosphere entirely, a super Greisen-Zatsepin-Kuzmin outlier that stared back at scientists from the data logs with what felt like cosmic contempt. This was not a particle that barely scraped over the line. It was one that vaulted over it with energy to spare, leaving the rules shattered in its wake. To account for such an impossibility, physicists had to venture into the realm of the radical, to ideas that sound more like science fiction than settled science. One haunting possibility involved dark matter, the invisible glue holding galaxies together. What if, scattered throughout the halo of our own Milky Way, there exist super-heavy dark matter particles, relics from the universe's first second? These hypothetical titans, billions of times more massive than a proton, could be slowly, quietly decaying. And in that decay, they might spit out a single, ordinary proton with all the concentrated fury of their ancient mass, a final burst of energy that would appear to us as an ultra-high energy cosmic ray born right in our galactic backyard. This would solve the travel problem instantly because the particle would not need to cross the vast, photon-filled intergalactic voids. It would be a local explosion of a ghost, a death rattle from the dark side of the cosmos happening all around us. An even more mind-bending explanation reaches for the fabric of reality itself. Some theories suggest space-time might not be perfectly smooth. On scales a billion times smaller than an atom, it could be foamy, churning with quantum defects or cosmic strings, flaws in the universe's underlying structure. If such a defect were to snap or vibrate catastrophically, it could release an immense burst of energy, channeling it directly into a single particle. This would mean cosmic ray 17 was not accelerated by any celestial object, but was a tear in the canvas of the cosmos, a glitch in the matrix made manifest as a subatomic bullet. These are not comfortable explanations. They are the kind of ideas scientists turn to only when every ordinary door has been slammed shut. They represent the frontier of desperation and genius, where the only way to explain a single point of data is to reinvent our picture of reality. Cosmic ray 17 stands as the purest example of defiance, a data point that does not ask for a refinement of our models, but for a revolution. The mystery of the 50 deepens with a pair of bullets that seem to arrive together. Cosmic ray 18 was not one, but two distinct ultra-high energy events captured by observatories within a span of just a few months. Their arrival directions, when traced back across the void, pointed to eerily similar patches of sky. To the scientists analyzing the data, this presented an electrifying possibility. Could these two cosmic rays be twins born from the same cataclysmic event? The idea of a transient source is compelling. Imagine a single, violent flash in the distant cosmos, a supernova exploding with unimaginable force, or two neutron stars spiraling together in a final, shattering embrace. Such an event would act as a colossal, one-time particle accelerator, firing a shotgun blast of high-energy matter in all directions. If two of those pellets, traveling for millions of years on nearly parallel paths, happened to strike Earth within a short window of each other, it would look exactly like this. Finding such a pair would be a monumental clue, a chance to tie a specific, catastrophic event to the cosmic rays we detect. It would move us from hunting for stationary objects to catching the universe in the act of a violent outburst. The challenge, however, lies in proving the connection. The first hurdle is energy. The two cosmic rays did not have identical power. One was significantly more energetic than the other. Is that a deal breaker? Not necessarily. A single transient explosion can produce a spectrum of particles, a range of energies like different-sized fragments from a single bomb blast. So a difference in energy alone does not rule out a common origin. The second, more daunting hurdle is composition. We do not know for certain if both particles were protons or ion nuclei or a mix. If one was a lightweight proton and the other a heavy ion nucleus, their journeys through the galaxy's magnetic fields would have been drastically different. The ion nucleus would have been bent and twisted far more severely, meaning their paths only appear to come from the same place by the time they reach us. Their true birthplaces could be light years apart, but the most profound challenge is time itself. Transient cosmic events are fleeting. A supernova's shockwave that can accelerate particles might only be effective for a few years, perhaps a few decades at most. Yet the travel time for these cosmic rays across intergalactic space is measured in millions of years. This creates a bizarre and counterintuitive scenario. For two particles to be from the same transient source, they would have had to be launched at virtually the same cosmic instant, within a tiny window of that explosion's active life. They would then travel across millions of light years, maintaining their tiny separation in arrival time, to finally hit Earth within months of each other. It is a staggering synchronization across eons. The odds seem astronomically low, yet with enough of these violent flashes happening across the universe, such a coincidence might not be impossible. The twin event mystery ultimately leaves us in a state of tantalizing uncertainty. It is a hint of a pattern, a whisper of causality in the random rain. But without knowing exactly what the particles are, or catching the afterglow of the explosion that might have created them, we cannot say for sure. These two cosmic rays could be siblings from a single catastrophic birth, or they could be perfect strangers from different corners of the universe whose paths converged at our planet by pure, meaningless chance. The line between a profound clue and a cosmic coincidence is heartbreakingly thin. The universe itself is a prison for the most powerful particles. This is the concept of the cosmic calorimeter, a grand and sobering idea that the cosmos is not empty, but filled with the faint, cold glow of the cosmic microwave background. This afterglow of creation acts as a kind of universal measuring cup, a calorimeter, that systematically drains energy from any ultra-high energy proton trying to cross intergalactic space. Every collision with one of these background photons is a tiny theft, a cosmic toll booth that every charged particle must pay on its million light-year journey. The Greisen-Zatsepin-Kuzmin cutoff is the final receipt, the maximum energy a proton can possibly have left after paying that toll across a vast distance. In this model, the energy of a cosmic ray is not just a number, it is a travelogue, a record of how far it has come and what it has endured. Enter cosmic ray 19, a particle captured with an energy that sits in a profoundly ambiguous zone. Its measurement was precise, placing it tantalizingly close to, but just below, the theoretical Greisen-Zatsepin-Kuzmin wall. This single data point becomes a cosmic riddle with two opposing solutions. The first interpretation is that it confirms the calorimeter model perfectly. This particle's energy, being just under the limit, suggests it is a textbook example of a proton that originated in a distant galaxy. It traveled for perhaps 100 million light-years, losing energy with every collision, until it arrived at our doorstep with exactly the amount of power the theory predicts for such a marathon runner. It would be a victory for our understanding, a quiet piece of cosmic machinery working exactly as advertised, but the second interpretation flips the script entirely. What if this particle is not a weary traveler from afar, but a local bullet? If its source is incredibly close within our own galactic neighborhood, it would not have had time to be slowed down by the cosmic calorimeter. It would arrive with almost all its original birth energy intact. In that case, its sub-cutoff energy is not a sign of a long journey, but a sign of a relatively weak nearby accelerator. It did not hit the limit because it never had to face the long road. So which is it? A distant messenger confirming our laws, or a local firecracker revealing a new class of nearby source? Cosmic Ray 19 offers no clear answer. It sits in the zone of maximum ambiguity, a data point that perfectly fits two completely different stories about the universe. This is the subtle tyranny of the cosmic calorimeter. It creates a rule so powerful that even the particles that seem to obey it might secretly be telling us the rule does not apply to them. The energy alone is no longer a simple clue. It is a mask hiding the true nature and origin of the bullet in a fog of perfect statistical coincidence. This magnetic maze is not a simple obstacle. It is the central character in the mystery. cosmic ray 20, a particle of staggering power detected by the Pierre-Auger Observatory, exemplifies the maddening puzzle. We know exactly where it appeared to come from, a precise coordinate on the celestial map. Yet that coordinate is a lie, a final address after a journey of unimaginable deflection. To find its true source, we must attempt to rewind its path through a universe we know is threaded with invisible magnetic force, a map we have only begun to sketch. The first layer of distortion comes from our own galactic backyard. As cosmic ray 20 entered the Milky Way, it plunged into the galaxy's own magnetic field. This field is not a neat bar magnet. It is a turbulent, spiraling web shaped by supernova explosions and the slow churn of billions of stars. Models of this field suggest the particle's path would have been bent by several degrees just in this final leg of its journey. That is enough to shift a potential source from one constellation to an entirely different one. But this is merely the local traffic. The real scrambling happens in the vast intergalactic voids. Here, magnetic fields are 1,000,000 times weaker, but they are stretched across hundreds of millions of light years. Their structure is one of cosmology's great unknowns. Are they tangled like spaghetti or organized into vast filamentary sheets tracing the cosmic web of dark matter? Each model paints a different possible history for our cosmic bullet. Running the rewind simulation under one model, cosmic ray 20 might have originated in a brilliant active galaxy 400 million light-years away. Under a slightly different model of magnetic turbulence, that same arrival direction points instead to a quiet, unremarkable galaxy cluster only 150 million light-years distant. A third simulation might send its path looping around a filament of the cosmic web, pointing to a source that, from our perspective, lies in the complete opposite direction of where we saw it arrive. This is the core of the impossibility. That single, clean data point, the arrival direction of cosmic ray 20, does not correspond to one source. It fans out into a cone of possibility, a spray of potential origins that could include dozens of galaxies, galaxy clusters, or vast stretches of seemingly empty space. The definitive explanation is not hidden, it is mathematically erased by the journey itself. We are left with a gallery of suspects, all with plausible alibis, and no way to determine which one fired the shot. The magnetic maze does not just hide the answer, it ensures that for now, and perhaps forever, the question of origin for events like this may have no single, satisfying solution. Cosmic ray 21 came from nothing. Its trajectory, traced back with the Auger Observatory's finest precision, led to a patch of sky that astronomers call a void. This was not just an empty direction, it was a profound cosmic quiet. Within a radius of 100 million light-years, a distance from which such a powerful particle should logically originate, telescopes found no major galaxies, no active black holes, no swirling stellar nurseries. It was a celestial desert, a volume of space so unremarkable it earned the nickname a nothing burger among frustrated researchers. This single event presents a trilemma, a three-pronged fork in the road where every path leads to a profound reassessment. The first possibility is that our maps are wrong. We pride ourselves on cataloging the nearby universe, but could an entire galaxy or a cluster of galaxies be hiding in that void, obscured by interstellar dust or simply too faint for our current telescopes to see? It is possible, but deeply unsettling, like discovering a major city missing from a satellite map of your own country. The second possibility is that our understanding of particle propagation is flawed. Perhaps magnetic deflection is even more extreme than our wildest models predict, bending the path of cosmic ray 21 through a 90-degree arc or more, sending it on a cosmic detour so vast that its true source lies in an entirely different, bustling part of the cosmos. This would mean our fundamental tool for this investigation, the particle's incoming direction, is worse than useless. It is actively deceptive. The third and most thrilling possibility is that the source is something we have not yet catalogued or even imagined. It could be an entirely new class of astrophysical object, dark and quiet, that does not emit the light we are trained to look for. Or it could be something more exotic, a defect in space-time or an echo of a process from the universe's first moments, acting as a silent particle gun in the apparent emptiness. The nothing burger direction is not an absence of evidence, it is evidence of absence, a quiet shout from the void that our inventory of the cosmos is desperately incomplete. A cosmic ray's death is not a single moment but a cascade of light. Cosmic ray 22 offered a strange signature in its final flash. While most detectors simply capture the total energy of an air shower, advanced observatories can dissect its birth in exquisite detail, recording the precise nanosecond by nanosecond unfolding of its ultraviolet pulse as it streaks across the sky. The profile of this particular event was a puzzle in its own right. It displayed an unusually short, sharp pulse duration. The entire cascade seemed to develop and extinguish faster than the models predicted. This tiny detail, a flicker in the data, is a whisper about the very first impact. When an ultra-high energy particle strikes the atmosphere, it does not just explode. It first strikes a single nucleus of nitrogen or oxygen, a direct hit that triggers the entire avalanche. The nature of that first collision and the particle that initiated it writes its signature into the light curve we observe. A short, fast pulse like this could mean several things. It might suggest the primary particle was a heavy nucleus like iron. Think of it like a tightly packed cluster of protons and neutrons. When a heavy nucleus hits the atmosphere, it acts less like a single bullet and more like a shotgun blast of subatomic pellets. Its many components can interact almost simultaneously, creating a shower that develops very quickly and intensely, but also fades faster because its energy is deposited in a more compact volume. Alternatively, a short pulse could hint at an unusual first interaction. Perhaps the particle struck the atmosphere at a very steep angle, plunging almost straight down, which compresses the timeline of the cascade. Or more speculatively, it could point to the primary particle being something exotic, a particle that interacts with matter in a way we do not fully understand, transferring its energy in a single, catastrophic burst rather than a more drawn-out process. These pulse anomalies are subtle, often buried in statistical uncertainties, but they are critical. They are the forensic details at the scene of a cosmic crime, the tiny splatter pattern that might tell us whether the bullet was a lone proton or a cluster of iron, fired from a steep angle or a shallow one. Cosmic Ray 22's brief flash adds another layer of cryptic data to the mystery, a reminder that even in death, these particles guard their secrets in the fine print of light. The faintest signal can be the most profound. After years of patient listening, the Pierre Auger Observatory detected a whisper not from a single source, but from the structure of the cosmos itself. It is called the large-scale anisotropy, a statistical pattern so subtle it emerges only when you map hundreds of ultra-high energy events against the night sky. The pattern is this: the arrival directions of these cosmic rays are not perfectly random. They show a weak but undeniable correlation with the positions of nearby galaxies, the grand architecture of the local universe. It is as if you listened to the patter of raindrops on a vast roof and realized faintly that they fell just a little more often over the rafters than over the spaces between. This is the most crucial clue we have. It tells us with growing confidence that the population of these particles is extragalactic. They are not born in our Milky Way, but are travelers from the island cities of stars that dot our cosmic neighborhood. This broad correlation is the context for our 50 specific mysteries. It means that Cosmic Ray 23 and every other extreme event is not a complete aberration. It is the most brilliant, most impossible member of a larger population whose general origin we now understand. The universe, in its broad strokes, is doing exactly what we expect, sprinkling these particles from the directions of mass, from the places where galaxies gather. Yet when we zoom in on any single spectacular bullet, that beautiful correlation breaks down. The map tells us the general neighborhood, but the address of the specific house remains maddeningly blank. So we are left with this elegant and frustrating duality. Statistically, we have solved the mystery. We know where they come from in the grand scheme. But individually, each one remains a ghost, a defector from the pattern whose specific birthplace is erased by magnetic winds and cosmic distance. The large-scale anisotropy confirms we are on the right trail, even as it makes the disappearance of each individual source all the more perplexing. One direction offers a different kind of violence, not from a single black hole, but from a frenzy of stellar birth. Cosmic Ray 24 presented an incoming path that pointed toward a nearby starburst galaxy, a place like Messier 82 or NGC 253. These are not the quiet, stately spirals of popular imagination. They are cosmic infernos, galaxies undergoing an explosive burst of star formation, where thousands of stars ignite in a relatively small volume of space. The appeal of a starburst galaxy as a source is visceral. Imagine a gigantic firework factory where explosions are not isolated accidents, but a continuous chain reaction of detonations. Each massive star that lives fast and dies young culminates in a supernova, whose shockwave blasts outward into the surrounding gas. In a starburst, these shockwaves overlap and collide, creating a turbulent, magnetized maelstrom that could act as a natural particle accelerator on a galactic scale. Instead of a single, monstrous engine like a black hole jet, the starburst hypothesis suggests a collective effort, a galactic wind driven by thousands of supernova that could, over time, whip particles up to these impossible energies. It is a compelling idea, a way to harness the combined fury of an entire galaxy's most violent stellar deaths. For Cosmic Ray 24, the alignment was promising. Its backtrack direction placed it within the error cone, the zone of possible origin of a known, powerful starburst galaxy. This was not an empty void, but a place teeming with the exact kind of astrophysical violence theorists had dreamed of. The association felt strong, a potential match between a cosmic bullet and a cosmic gun that actually made sense. Yet, even this promising lead lacks a definitive signature. The alignment is not perfect, and the magnetic scrambling we have discussed could still mean the particle was merely passing through that general neighborhood, not born there. Furthermore, the starburst model, while powerful, has its own energy limits. Can a galactic superwind truly push a single proton to 200 exaelectron volts, or would it require conditions even more extreme than we observe? Most tellingly, if starburst galaxies were the dominant source of these ultra-high energy events, we would expect to see many more of our 50 cosmic rays pointing toward them. We do not. While Cosmic Ray 24 offers this tantalizing direction, the majority of the other events point elsewhere, to voids and quiet patches of sky. So the starburst galaxy remains an excellent suspect for this one case, a brilliant example of how cosmic violence might be harnessed, but it cannot be the universal answer. Its very specificity highlights the broader problem. The universe seems to employ many different methods, or perhaps one utterly mysterious method, to create its most powerful particles. Each clue that seems to solve the mystery for one event only deepens it for all the others. The blazar is a cosmic searchlight aimed directly at our planet. Among the most violent objects in the universe, these are active galaxies whose central black hole fires a jet of plasma and radiation so precisely aligned with our line of sight that it appears terrifyingly bright. When an ultra-high energy cosmic ray seems to arrive from the direction of one of these monsters, the case feels compelling, almost closed. This is the story of Cosmic Ray 25. Its reconstructed path pointed with intriguing precision toward a known blazar, a BL-Lacerty object. These are a special class of blazar whose jets are so intense they drown out the light of the surrounding galaxy, leaving only a brilliant, fluctuating point of light in our telescopes. They are considered some of the universe's most efficient natural particle accelerators, with magnetic fields and shock waves within those relativistic jets capable of whipping protons to staggering speeds. For cosmic ray 25, the alignment was too good to ignore. Here, at last, was a suspect with a perfect motive and a weapon pointed right at us. The logic was beautiful. A blazar's jet is a focused beam. If it can accelerate particles to ultra-high energies and that beam is aimed at Earth, then we should be in the direct line of fire, a perfect target for its most powerful projectiles. This specific event became a key data point for researchers arguing that blazars are the dominant sources of these mysterious rays. The correlation seemed powerful, a direct link between a theoretical engine and an actual bullet caught in flight. Yet the controversy runs deep because for every study that finds a tantalizing link, another finds only empty noise. Skeptics point out a critical problem, the curse of statistics. The sky is filled with bright objects from blazars to other active galaxies. If you have a handful of cosmic rays arriving from random directions, pure chance dictates that a few of them will, by accident, line up with something interesting in the sky. It is like throwing darts at a map of the world and finding one landed on a major city. The alignment feels meaningful, but it might just be luck. To prove a true connection, you need many more darts landing consistently on that same city, a pattern that rises far above random chance. With only 50 of these ultra-high energy events on record, the sample size is agonizingly small. Furthermore, even if cosmic ray 25 was accelerated by that blazar, the million-year journey through intergalactic magnetic fields would have bent its path. The perfect alignment we see today might be a final coincidence after a long, curved voyage, meaning the true birthplace could still be elsewhere. The debate over blazars is a microcosm of the entire mystery. We have a perfect theoretical culprit, a dramatic candidate source that fits the narrative of cosmic violence. We have individual events that seem to finger that culprit directly. But we lack the overwhelming statistical evidence to secure a conviction. Cosmic ray 25 stands at the center of this tension, a single point of light that either illuminates the path to an answer or simply highlights how desperately we want to see a pattern in the glorious random rain. The heart of our own galaxy holds a silent, sleeping giant. Cosmic ray 26 presented a trajectory that seemed to glance toward the Milky Way's crowded core, the direction of Sagittarius, a star, the supermassive black hole that anchors our entire spiral of stars. At 4 million times the mass of our Sun, it is a monster by any measure, yet it is remarkably quiet today, a dormant engine emitting only faint whispers of radiation. This makes it an unlikely suspect for creating the universe's most powerful particles, but in a mystery this profound, no possibility is ignored. The idea is not that Sagittarius, a star, is actively firing bullets at us now, but that it might have in the distant past. Galactic archaeology suggests our central black hole has not always been so serene. There is evidence buried in the gas clouds and stellar orbits around it of past outbursts, periods of frenzied feeding when it would have been an active galactic nucleus, blazing with light and spewing jets of plasma. If such an outburst occurred even a few million years ago, the shock waves from that ancient violence could still be propagating through the halo of our galaxy, acting as a vast, slow-moving particle accelerator. A single proton caught in the right place at the right time within that fading shockwave could theoretically be whipped up to an ultra-high energy and flung in our direction. This is a cosmic long shot, a hypothesis built on echoes of echoes. The alignment of cosmic ray 26 with the galactic center is almost certainly a coincidence, a chance overlap given the dense star fields in that direction. The particle's immense energy almost guarantees an extragalactic origin, far beyond the power of even an awakened Sagittarius, a star. Yet scientists meticulously modeled the possibility anyway. They asked, could our own home galaxy's heart have been the gun? The answer was a near certain no, but the exercise was never about finding the source for this one event. It was about discipline. It exemplifies the exhaustive nature of the hunt, the process of elimination that defines true scientific inquiry. Every potential source, no matter how improbable, must be considered and tested before it can be ruled out. This thoroughness is what transforms a collection of shocking anomalies into a coherent, if baffling, field of study. By proving, through careful calculation, that even our galaxy's central black hole is not the culprit, researchers narrow the search further, pushing the true answer farther out into the deep, dark fields between the stars. The glance toward home only deepens the certainty that the solution lies in the great, wide unknown. Sometimes the bullet itself is the greatest clue. Cosmic Ray 27 arrived not as a confirmation of a theory, but as a quiet executioner for some of the most exotic ideas in physics. This particle became a crucial test for what are known as top-down theories. The name is a perfect description of their logic. Instead of the traditional bottom-up approach, where a cosmic engine like a black hole or colliding galaxies slowly builds up a particle's energy over time, top-down theories suggest these cosmic rays are not accelerated at all. They are born at the peak of power as decay products from something unimaginably ancient and massive. Imagine finding a diamond on a beach. The bottom-up approach says it was formed by the slow geological pressure of the Earth. A top-down theory suggests it fell from the sky, a shard of a shattered asteroid that was already a diamond when it entered the atmosphere. For cosmic rays, these theoretical parent objects are relics from the universe's first moments. They could be super-heavy dark matter particles, billions of times more massive than a proton, quietly decaying in the halo of our galaxy. Or they could be topological defects, cracks or knots in the very fabric of spacetime formed when the fundamental forces of nature froze into their current state during the Big Bang's cooling. If such a defect were to snap or unravel, it would release a catastrophic burst of energy, creating a spray of ultra-high energy particles directly, with no accelerator required. These are beautiful, radical ideas, but they come with a specific prediction. The decay of these primordial monsters would not just produce protons, it should also create a shower of other particles, particularly ultra-high energy photons and neutrinos in a predictable ratio. The signature of a top-down event would be a cosmic ray accompanied by a specific chorus of these ghostly partners. Cosmic Ray 27 was captured with exquisite detail. Its energy was immense, its direction recorded. The moment it was detected, scientists immediately checked the data from neutrino telescopes and gamma-ray observatories. They listened for the echo, for the phantom photons and neutrinos that should have arrived alongside it if it were the product of a decaying dark matter particle or a snapping cosmic string. The result was a profound silence, no associated neutrinos, no ultra-high energy photons, just the lone, defiant bullet. This non-detection was a verdict. It did not rule out all top-down models, but it decisively eliminated a whole class of them. The universe, in this one specific instance, refused to play along with the most elegant exotic scripts. This is how each of these 50 events shapes our understanding. They are not just mysteries to be solved, they are tools. Every precise measurement, every anomalous pulse of light, and every absent neutrino acts as a constraint, a wall that future theories cannot cross. Cosmic Ray 27 built one such wall, forcing physicists to refine their most speculative dreams and acknowledge that the truth, whatever it is, must be stranger than even their wildest fiction. The bullet killed the theory, but in doing so, it carved a clearer path through the wilderness of the unknown. The most powerful events exist on a spectrum of cosmic violence. To understand the 50, we must see them not as isolated freaks, but as the extreme end of a continuous, whispering rain that has been falling on Earth for billions of years. The vast majority of cosmic rays are low energy, born within our own galaxy from supernova shockwaves. As you climb the energy ladder, their numbers drop off steeply, a predictable decline until you hit a curious bump around 5 exa-electron volts. This is the ankle of the cosmic ray spectrum, a subtle flattening in the graph that has profound meaning. Think of it like listening to a waterfall. The constant roar is the low-energy galactic cosmic rays. The ankle is the moment you start to hear a distinct, distant river joining the noise from much farther away. This feature is widely believed to mark the transition point. Below the ankle, the particles are predominantly galactic, confined to the Milky Way's magnetic prison. Above the ankle, the floodgates open to the extragalactic universe. Here, the particles have enough energy to fight free of our galaxy's magnetic grip and arrive from the vast cosmos beyond. This makes every cosmic ray detected just above this boundary a special kind of key. Cosmic Ray 28, one of our 50, carried an energy that placed it squarely in this transitional zone, just a few steps above the ankle. It was not a record-breaking monster, but its position on the spectrum makes it a critical piece of the puzzle. This particle represents a scout from the frontier, one of the first emissaries from the extragalactic realm. Studying events like it helps us calibrate the models of how particles escape galaxies and begin their long, scrambled journeys through intergalactic space. It helps us understand the magnetic walls of our own galactic home and the point at which the universe's larger accelerators begin to dominate the signal. So while we rightly marvel at the "oh my God" particles that scream in from the void, we must also listen carefully to the whispers just above the ankle. They are the border guards of this mystery, showing us where the map of the known ends and the territory of the truly impossible begins. The microscopic battle begins with a phantom, a single photon left over from the Big Bang. This particle of light, part of the cosmic microwave background, has been drifting for 13 billion years, its energy faded to a whisper. Yet for an ultra-high energy proton screaming across the universe at nearly the speed of light, this phantom is a brick wall. This is the quantum mechanical heart of the Greisen-Zatsepin-Kuzmin limit, a process called pair production. When the proton, moving with such ferocious energy, slams into one of these background photons, the collision is not a simple bump. The immense energy of the proton can be converted directly into mass, following Einstein's most famous equation. In a flash, the photon and a piece of the proton's energy vanish, replaced by two new particles born from pure violence, an electron and its antimatter twin, a positron. This is pair production, and for the proton, it is a robbery. Each collision strips it of a fraction of its precious speed, slowing it down over millions of light years until it falls below the theoretical cutoff. This is the inevitable fate that should await every ultra-high energy proton on a long intergalactic journey. Cosmic Ray 29, an event with energy measured tantalizingly close to that cutoff, forces us to stare directly at this quantum battlefield. Its very existence is a question mark hovering over the entire process. To have arrived with that energy, one of three things must be true. First, it could be a cosmic lottery winner, a proton that, against all odds, managed to travel a vast distance without hitting a single photon in just the right way to trigger pair production. Imagine firing a bullet through a dense fog where every droplet can stop it, and having the bullet emerge unscathed on the other side. It is possible but staggeringly unlikely. Second, it could mean the proton did not have to run the gauntlet at all. If its source is extremely close to our galaxy, it simply did not have enough time or distance to suffer the relentless attrition of pair production. Its energy is not a survivor's trophy, but a sign of a short commute from a nearby, hidden accelerator. The third possibility is the most profound, that our understanding of the pair production process itself is incomplete. Perhaps at these extreme energies, the rules of quantum electrodynamics bend in ways we have not yet predicted. Maybe the proton interacts with the photon C less frequently than our equations state, or finds a quantum loophole that allows it to slip through the net. Cosmic Ray 29 is a single data point sitting on a razor's edge, a particle that by all accounts should have been slowed, yet appears at our doorstep still carrying the echo of an impossible power. It does not shout its origin like the "oh my God" particle. It whispers a deeper, more technical secret about the fabric of space and the rules of engagement on the cosmic scale. The data from the giants does not always agree. As the Pierre-Auger Observatory in the south and the telescope array in the north continue their patient watch, a subtle tension has emerged in their findings. It is not a dramatic conflict, but a quiet disagreement in the numbers, a reminder that even our most powerful instruments are still learning how to see. This is the story of Cosmic Ray 30, not a single event, but a collective tension over the shape of reality itself. One of the most critical points of comparison is the precise location of the Greisen-Zatsepin-Kuzmin cutoff, that cosmic cliff where the highest energy particles should vanish. Both observatories confirm the cliff exists, but they do not perfectly agree on where the edge is. The Auger data suggests a steepening, a dramatic drop-off beginning at an energy of about 40 exa-electron volts. The telescope array data, however, points to a cutoff that might be slightly higher, perhaps around 57 exa-electron volts. The difference seems small on a logarithmic scale, but in the precise world of particle physics, it is significant. It is the difference between the universe applying the brakes a little sooner or a little later in the particle's journey. This discrepancy could stem from subtle differences in how the two experiments calibrate their energy measurements. Each uses a different technique, a different set of atmospheric models and detector responses to translate a flash of light or a cascade of particles into a definitive number. It is like two master watchmakers trying to measure the same event with different, incredibly complex clocks. They will almost always agree on the hour, but might disagree on the exact second. This tension forces an essential humility. The mystery is not just out there in the cosmos, it is also here, in the painstaking work of achieving perfect experimental consensus on Earth. Another point of gentle friction lies in the maps of the sky. Both observatories see large-scale patterns, anisotropies hinting that cosmic rays are not arriving randomly. But the specific hotspots they report, while compelling, do not perfectly mirror each other across the celestial equator. The strength and clarity of these patterns, the statistical confidence with which we can say they are real, varies between the two datasets. This could mean the northern and southern skies are genuinely different, that the universe's particle accelerators are not evenly distributed. Or it could again reflect the challenges of comparing two different instruments, each with its own unique field of view, exposure time, and sensitivity to different types of particles. The pursuit of Cosmic Ray 30, this collective tension, is not a sign of failure. It is the sound of science working at its absolute limit. Every disagreement is a question, and every question refines the next generation of experiments. It tells us that solving the mystery of the 50 will require more than just collecting data. It will require a perfect, shared understanding of what that data means. The giants are in conversation, and their dialogue is slowly, meticulously carving the truth out of the void. A faint crackle of static holds the key to the universe's greatest bullets. While the giants watch for flashes of light or listen for particle impacts, a new generation of detectives is tuning into a different frequency entirely, the radio waves generated by the death of a cosmic ray. This is the radio revival, a technological leap that listens to the sky's quietest whispers. When an ultra-high energy particle strikes the atmosphere, the resulting avalanche of electrons and positrons does more than just glow. As these charged particles are whipped back and forth by Earth's own magnetic field, they emit a faint but coherent pulse of radio waves, a nanosecond-long chirp across the FM band. For decades, this signal was considered background noise, an inconvenient static to be filtered out. Now it is the star witness. Vast arrays of simple radio antennas like the Low Frequency Array or LOFR spread across Europe have turned their electronic ears to the sky. They do not wait for clear nights. They can listen through clouds day or night, capturing the radio fingerprint of each cosmic ray shower with breathtaking precision. Cosmic Ray 31 was one such event, a particle of immense energy whose arrival was not seen first but heard. As it shattered the atmosphere, hundreds of LOFR antennas recorded the exact shape, polarization, and strength of its radio pulse. This data is a treasure trove because the radio emission is generated by the motion of the charged particles in the shower. Its signal is exquisitely sensitive to the entire cascade's development. Scientists can use it to reconstruct the shower in 3 dimensions with a resolution far beyond what traditional fluorescence telescopes can achieve. They can pinpoint the depth in the atmosphere where the shower reached its maximum size, a critical number that acts as a fingerprint for the primary particle. A proton shower reaches its peak higher up, an iron nucleus lower down. For Cosmic Ray 31, the radio pulse painted a clear picture, suggesting with new confidence that this particular bullet was likely a proton, not a heavy nucleus. This single piece of information cuts through decades of ambiguity. Knowing the composition changes the entire investigation. If it was a proton, then the magnetic scrambling it endured on its journey was less severe, meaning the direction we observed is closer to its true origin. That empty patch of sky it seemed to come from might be a more reliable address than we thought, forcing us to look harder at the nothingness. The promise of this technique is monumental, and it points to a future where the entire sky is a radio ear. The planned square-kilometer array, a global network of thousands of antennas, will be so sensitive it could detect these radio whispers from cosmic rays with even higher energies, events so rare they might fall only once per century on a detector the size of Augur. This new window does not just offer more data, it offers a different kind of sight, one that might finally decode the cryptic messages these 50 particles have carried across the void. But our atmosphere is a veil, a beautiful and frustrating filter for the universe's secrets. To truly see the reign of the most impossible particles, we must rise above it. This is the dream behind Cosmic Ray 32, a vision not of a detector on the ground, but an observatory in the void of space itself. Projects like the Japanese experiment module Extreme Universe Space Observatory, or JEME-USO, were designed with one audacious goal: to turn the International Space Station, or a dedicated satellite, into the ultimate cosmic ray hunter. Its method is elegantly simple yet revolutionary. Instead of looking up through the murky atmosphere from below, it would look down from orbit. Its wide field of view cameras would stare at the dark side of Earth, watching not for stars, but for the brief, enormous flashes of ultraviolet light created when an ultra-high energy cosmic ray slams into the atmosphere. From that vantage point, 400 kilometers high, it would see the entire fluorescence glow of a giant air shower spread out like a blooming flower across 1,000 square kilometers of sky, all in a single glance. The potential of such a perspective is staggering. A space-based observatory would not be limited by the curve of the Earth or the footprint of a ground array. Its effective collection area could encompass millions of square kilometers, turning it into a net thousands of times larger than the Pierre Auger Observatory. For the rarest cosmic rays, the ones with energies so high they might fall only once per century on a continent-sized detector, this is the only way to gather meaningful statistics. We would no longer be waiting decades for a single, shocking data point. We could begin to see a population, a distribution, a true picture of the universe's most extreme accelerators. One of our 50 mysteries, a cosmic ray whose energy and direction have defied every attempt at explanation, is precisely the kind of event such a mission was born to solve. It represents the frustrating present where we have a breathtaking anomaly but not enough siblings to understand its family. A space observatory would seek out dozens, perhaps hundreds, of events just like it, allowing scientists to finally perform the forensic work that is impossible with a sample size of one. They could ask, do all particles of this impossible energy come from similar empty patches of sky? Do they share a common pulse profile or composition? Or do they scatter randomly, revealing a zoo of different sources? The technical challenges of this dream are as immense as the particles it hunts. Building a hypersensitive ultraviolet telescope that can operate in the harsh environment of space, distinguishing the faint, nanosecond glow of a cosmic ray from the constant flicker of city lights, auroras, and lightning, is a feat of engineering that pushes the boundaries of the possible. Yet the pursuit continues with new proposals and prototypes, because the prize is nothing less than a new sense for our planet. We will be giving the Earth a pair of eyes that see in the light of dying universes, watching for the largest explosions in creation to write their signatures across our own sky. The story of Cosmic Ray 32 is not about a particle we have caught, but about the leap of faith we must take to catch its kin. It is the promise that to solve a mystery written in bullets from the void, we must finally step outside and watch for the muzzle flash. A cosmic explosion leaves more than one kind of echo. In the last decade, we have entered a new age of cosmic observation called multi-messenger astrophysics. It is the practice of listening to the universe with every sense we have at once. When two neutron stars collide, they do not just release a flash of light. They send out ripples in space-time called gravitational waves, detectable by observatories like LIGO and Virgo. They also fire a burst of neutrinos caught by detectors like IceCube. And in theory, they could accelerate protons to incredible speeds, creating an ultra-high energy cosmic ray. The dream is to catch all these messengers from a single, catastrophic event, to triangulate the source with perfect precision, and finally understand the engine behind the violence. This brings us to Cosmic Ray 33, one of our 50 mysterious bullets. Its arrival was recorded with a clear time stamp and a precise direction. Immediately, scientists performed a crucial check. They combed through the data from gravitational wave observatories and neutrino telescopes, searching the hours, days, and even weeks around that moment for any signal from the same general patch of sky. They were looking for a cosmic handshake, a confirmation that this lone particle was part of a larger chorus. The result was a profound and telling silence. No gravitational wave chirp, no high-energy neutrino, just the single, defiant cosmic ray. This non-detection is not a failure, it is a powerful piece of information. It tells us that Cosmic Ray 33, and likely many of its kin, are probably not the children of the most dramatic transient events we have learned to see. It suggests they were not born in a neutron-star merger or a brilliant supernova that also shook the fabric of space-time. The accelerators that create these particles operate on a different timescale or in a different way. Perhaps they are not the result of a single, brilliant detonation, but the product of a slow, relentless process, like particles being whipped around for centuries in the turbulent lobes of a radio galaxy. Or maybe the cataclysm that created it was so distant or so perfectly beamed away from Earth that its gravitational waves and neutrinos were too faint for our current instruments to catch. The multi-messenger mist deepens the isolation of these events. They are not just arriving from empty space, they are arriving without an entourage, without the company we would expect from the universe's most famous forms of violence. This forces us to broaden the search to consider quieter, more patient, or more exotic cosmic engines that operate in the dark, leaving only a single, impossibly powerful bullet as their only calling card. The very air we breathe is a lens that distorts the cosmic signal. While we look millions of light years into the void for answers, one of the greatest sources of uncertainty in this entire investigation hangs just a few miles above our heads in the thin, shifting blanket of Earth's own atmosphere. This is the weather factor, a subtle but profound variable that touches every single one of our 50 mysteries, including Cosmic Ray 34. When a particle from the depths of space strikes, it does not interact with a perfect, sterile laboratory vacuum. It hits a dynamic, living atmosphere. The temperature, pressure, and humidity on that particular night at that particular altitude change everything about the cosmic ray's final message. Take the process of fluorescence, that telltale ultraviolet glow our telescopes capture. Nitrogen molecules in the air get excited by the particle cascade and release light. But how much light they release, the fluorescence yield, depends directly on the density of the air. On a cold, high-pressure night, the air is denser. The excited nitrogen molecules collide with their neighbors more frequently before they can emit their light, quenching the glow slightly. On a warm, low-pressure night, the air is thinner and the fluorescence can shine a bit brighter. A difference of just a few percent in the measured light can translate into a significant error in calculating the primary particle's energy, potentially shifting it above or below a critical threshold like the Greisen-Zatsepin-Kuzmin limit. For cosmic ray 34, the uncertainty introduced by the atmosphere was a central part of its story. The event was detected on a night of unusual meteorological activity. A high-altitude weather balloon launched from a nearby station recorded a thin, persistent layer of cirrus clouds at precisely the altitude where the air shower reached its maximum development. Those ice crystals did not block the ultraviolet light, but they scattered it, subtly blurring the precise image of the cascade that the fluorescence telescopes captured. Furthermore, a passing pressure front meant the temperature profile of the atmosphere that night was not the standard model assumed by the analysis software. Scientists had to go back to raw weather data, to minute-by-minute readings from balloons and satellites, to build a custom atmospheric model for that specific 6-hour window over the observatory. They ran the numbers again, feeding in the true conditions. The energy estimate for cosmic ray 34 shifted. It did not change by orders of magnitude, but it moved by a meaningful amount, enough to alter its ranking among the most extreme events and tweak the angle of its incoming trajectory by a fraction of a degree. This recalibration is not a flaw in the science, it is the science. It is a humbling reminder that to read a message from the edge of the universe, we must first learn to read our own sky with exquisite care. Every ultra-high energy cosmic ray is filtered through a lens of swirling wind and drifting cloud, and extracting its pure cosmic truth requires the painstaking work of untangling it from Earth's own beautiful, messy variables. The universe is never silent. Beneath the rare, shattering impact of an ultra-high energy cosmic ray, there exists a constant, gentle drumbeat, a rain of lower energy particles that has fallen upon Earth for all of life's history. This is the cosmic ray background, a sea of protons and atomic nuclei from our own galaxy, each carrying a tiny fraction of the energy of our 50 mysteries. For the detectors hunting those singular, impossible events, this background is a relentless noise, a static hiss that must be perfectly understood and filtered out. Every second, thousands of these lower energy particles streak through the atmosphere, creating small, unremarkable showers. The giant observatories are designed to ignore them, setting electronic thresholds that only the largest, most violent cascades can trigger. It is like trying to listen for a single, distant shout in a crowded, roaring stadium. You must first learn the exact sound of the crowd, so you can recognize the moment it is broken. This brings us to cosmic ray 35, an event that arrived not with a scream, but as a whisper that almost got lost in the noise. Its measured energy was right on the precarious border between the extraordinary and the ordinary, a gray zone where the background static is loudest. For the scientists analyzing its data, a nagging question arose, one that haunts every frontier of detection. Could this be a ghost in the machine, not a message from a cosmic monster, but a cruel statistical fluke, a perfect storm of background noise that merely mimicked the signature of something far greater? Imagine the cosmic ray background as a chaotic sea. Most waves are small, but occasionally, by pure chance, several smaller waves can arrive at the exact same moment and place, stacking their energy to create a single, towering rogue wave. To a detector on the shore, that rogue wave looks unique, a record-breaking event. But it is not a true monster from the deep, it is an illusion born of coincidence. For cosmic ray 35, researchers had to exhaustively test this possibility. They modeled the behavior of the background rain with immense computational power, simulating trillions of possible interactions. They asked, how likely is it that 2 or 3 lower energy cosmic rays, arriving within nanoseconds of each other from slightly different angles, could strike the detector array in such a perfect pattern that their signals would merge into a single, seemingly ultra-high energy event? The answer was a very small number, but not 0. In a universe of constant particle rain, even the most improbable coincidences will eventually happen. To rule out this ghost, they turned to the finer details. A true ultra-high energy cascade has a specific, smooth shape as it develops through the atmosphere. A merged event, a Frankenstein's monster of background noise, would have a jagged, inconsistent profile. The data from cosmic ray 35 was scrutinized for any such telltale jaggedness, any hint of multiple cores in the shower. After weeks of analysis, the consensus was that it was real, a genuine particle from the frontier, but the exercise was never about this one event alone. It was a ritual of scientific rigor, a reminder that before we can accept the impossible, we must first prove it is not merely the improbable wearing a clever disguise. The background blur is not just noise to be eliminated, it is the canvas upon which these brilliant, defiant signatures are painted, and knowing its every shade is the only way to trust the masterpiece. A violent ripple in space-time might have left a bullet in its wake. On August 17, 2017, gravitational wave observatories felt the universe shudder. 2 neutron stars, each a city-sized corpse of a dead star, spiraled together and merged in a galaxy 130 million light-years away. The event, catalogued as GW170817, was a landmark in multi-messenger astronomy, seen in gravitational waves, gamma rays, and light across the spectrum. It was a kilonova, a cosmic forge that created gold, platinum, and other heavy elements in its radioactive debris. But could such an event also forge the universe's most powerful particles? This is the speculative thread that ties to cosmic ray 36, an ultra-high energy event detected with an arrival direction that, when its path is blurred by magnetic deflection, falls within a vast cone of possibility pointing back toward that general region of the cosmos. The timing is the first tantalizing hook. The cosmic ray was detected months after the gravitational wave signal. Given a travel distance of 130 million light-years, a particle launched at nearly the speed of light from that merger would arrive roughly 130 million years later. But in our frame of reference, the light, the gravitational waves, and a potential cosmic ray from the same cataclysm would all wash over Earth within a human lifetime, separated only by the slightly different speeds and paths of their journey. The coincidence in time and rough direction is provocative, a whisper of a connection. The physics, however, is where the speculation ignites. A neutron-star merger is not a gentle event. In its final moments, it can launch relativistic jets, narrow beams of plasma moving at over 99% the speed of light. These jets are prime candidates for particle acceleration. Theorists suggest that in the chaotic aftermath, shockwaves rippling through these jets or through the expanding debris cloud could act as natural particle colliders, trapping protons or atomic nuclei and whipping them back and forth in turbulent magnetic fields. Over days or weeks, this process could, in theory, boost a tiny fraction of particles to the staggering energies we classify as ultra-high energy. It is a cosmic version of cracking a whip where the tip of the lash, the particle, reaches an impossible speed. Yet for cosmic ray 36 to be that particle, the jet would have needed to be pointed almost precisely at Earth, a 1 in a million alignment. Even a slight misalignment would mean the beam of accelerated particles shot harmlessly off into the void, missing us entirely. Furthermore, the energy required pushes the very limits of what such a transient event is believed capable of. A merger is powerful, but is it powerful enough to create a particle that defies the Greisen-Zatsepin-Kuzmin limit? Many models say no, that the engines needed for such feats are larger and more long-lived, like the cores of active galaxies. The link between cosmic ray 36 and that distant kilonova remains a beautiful, fragile hypothesis. It represents the cutting edge of cosmic detective work, where we take a known cataclysm and a mysterious bullet and ask if they could possibly be family. The answer is still written in uncertainty, but the mere possibility changes how we listen to the cosmos. It means that every time we feel a ripple in space-time, we must now also listen for the echo of a single, silent impact, a ghost from a golden explosion that might have sent a piece of itself across the ages to find us. The dark matter halo of our own galaxy could be a silent particle gun. This is the radical promise of the decay hypothesis, a way to solve the mystery of the 50 without ever finding a source in the sky. Picture our Milky Way not just as a disk of stars, but as a vast spherical cloud of invisible matter, a halo of particles that neither emit nor reflect light. Now imagine that within this halo, scattered like ancient landmines from the Big Bang, are super-heavy dark matter particles. These are not the light, wispy candidates some theories propose. These would be titans billions of times more massive than a proton, relics from the universe's first moments, and they are unstable. Over eons, they spontaneously decay, vanishing in a flash of pure energy that condenses into a spray of ordinary particles, including a single, furious proton. This proton, born with all the energy of its decaying parent, would then zip straight toward Earth. Its journey would be short, entirely within our galaxy, so it would not be slowed by the cosmic microwave background. Its arrival would be a random event coming from any direction in the sky, since the dark matter halo surrounds us completely. Cosmic ray 37 is the kind of event that makes this idea so seductive. Its energy was immense, placing it firmly among the defiant outliers. More intriguingly, its arrival direction was not from any known structure or active galaxy. It came from a quiet, high galactic latitude, a place where the stellar disk of the Milky Way is thin. This fits the dark matter halo model perfectly, a random decay from the spherical cloud above the galactic plane. The appeal is profound. It eliminates the need for a cosmic accelerator altogether. We would not need to find the empty gun because the bullet materializes out of the invisible fabric of our own home. The mystery of the 50 would become a local phenomenon, a whisper from the dark side of our own galaxy. Yet for all its elegance, this hypothesis faces a brutal statistical challenge. If such decays are happening frequently enough to produce the few ultra-high energy cosmic rays we see, they should also be happening everywhere in the halo. And the halo is densest at the very center of our galaxy, in the region of Sagittarius, a star. If decays are random, we should see a strong, unmistakable excess of these events arriving from the direction of the galactic center, a bright spot on the cosmic ray map. We do not. The data shows no such concentration. The arrival directions of our 50 mysteries are isotropic, evenly sprinkled across the sky, with no significant pile up toward the Milky Way's core. This is a major, perhaps fatal, drawback. It means either the dark matter is not distributed as we believe, or these decays are not the source. Furthermore, as we saw with cosmic ray 27, the expected byproducts of such decays, like ultra-high energy photons and neutrinos, are also missing from our observations. The dark matter decay dangle remains a beautiful idea, a theoretical life raft in a sea of impossible data. But until it can explain why the galactic center is silent and where the phantom photons are, it remains a tantalizing dead end, a ghost of a solution that haunts the edges of the mystery without ever stepping into the light. The fabric of reality itself might have a flaw, a crack that just snapped. This is the realm of cosmic strings, hypothetical threads of pure energy thinner than an atom but stretching across the entire universe, left over from its violent first moments. Think of the early cosmos as a pot of water cooling. As it transitions from a chaotic boil to a calm, uniform state, the water can freeze with imperfections, with cracks and fissures trapped in the ice. Cosmic strings would be those cracks in the frozen structure of space-time, one-dimensional defects of unimaginable density. And according to some of the most speculative theories in physics, if one of these cosmic strings were to vibrate catastrophically or snap, the release of energy would be beyond comprehension. It would not be an explosion in space, but a rupture of space itself. From such an event, a spray of ultra-high energy particles could be born directly, with no need for a black hole or a colliding galaxy to accelerate them. They would emerge fully formed at the peak of power, like sparks flying from a severed power line made of pure space-time. Cosmic Ray 38 represents the kind of event that drives physicists to consider such breathtaking possibilities. Its energy, its isolation, its arrival from a celestial nowhere all defy every conventional engine we can name. When the standard catalogue of cosmic monsters fails, the imagination must reach further into the quantum foundations of reality. The cosmic string snap is not a mainstream theory. It is fringe physics of the highest order, a mathematical ghost that haunts the equations of the very early universe. No one has ever detected a cosmic string, and their existence remains a beautiful, untested prediction. Yet theorists explore it because it represents a logical endpoint of desperation and creativity. When you have 50 bullets that cannot be traced to any gun, you must eventually ask if the bullets are not being fired at all, but are instead being spontaneously created by the snapping of the universe's own hidden bones. This idea serves as a mirror, reflecting just how far beyond known astrophysics these 50 events have pushed us. They are not merely puzzles, they are provocations, daring us to rewrite not just our maps of the cosmos, but our understanding of its very fabric. The uncertainty is not just about where they come from, but what they even are. Cosmic Ray 39 was captured with stunning clarity by the Pierre Auger Observatory's fluorescence eyes, its ultraviolet death streak painted across the night. The shape of that light curve, the precise way the cascade grew and faded in the atmosphere, was a perfect fingerprint, and it was a blurry one. The data did not point decisively to a single, lightweight proton. Instead, the shower profile sat uncomfortably between two possibilities. It was consistent with a proton that had plunged into the atmosphere at a slightly steeper angle than average. But it was equally consistent with something much heavier, like a nitrogen nucleus or even an iron nucleus arriving on a more shallow path. This single piece of ambiguity ripples out to distort every other question we ask. Think of it as a cosmic crime scene where we cannot tell if the bullet was a small caliber round or a heavy slug. That one fact changes the entire investigation. If it was a proton, its single positive charge means it was only gently nudged by intergalactic magnetic fields. The direction we saw it come from is relatively trustworthy, perhaps only a few degrees off from its true birthplace. Our search for the source can focus on a narrower cone of sky, but if it was an iron nucleus with 26 times the electric charge, the story shatters. That immense charge makes it a puppet to magnetic forces. Its path could have been bent and twisted through an arc of 30 degrees or more over its journey. The seemingly empty patch of sky it came from is a complete illusion. The true accelerator could be hiding in an entirely different constellation, its signals scrambled beyond recognition. This composition conundrum also rewrites the requirements for the cosmic gun itself. Accelerating a single proton to such impossible energy is hard enough. But accelerating an entire iron nucleus, a tightly bound cluster of 56 protons and neutrons, to the same breathtaking speed requires an engine of even more monstrous focused power. It suggests a different kind of cosmic violence, perhaps the turbulent shock waves in the colossal lobes of a radio galaxy, where heavier elements can be trapped and whipped to extremes. So with cosmic ray 39, we are left staring at a perfect dead end in the data. We have the bullet's energy, we have its arrival time, we have the direction it appeared from. But without knowing its fundamental identity, we cannot map its past or understand the force that created it. The particle is a locked door, and the key is a secret it destroyed upon impact with our own air. The ultimate speed limit might not be absolute. For over a century, Einstein's theory of special relativity has been the bedrock of physics, establishing the cosmic speed limit of light and the principle of Lorentz invariance. This principle states that the laws of physics are the same for all observers, no matter how fast they are moving. It is why a proton's behavior is predictable and why the Greisen-Zatsepin-Kuzmin limit is such a formidable wall. But what if that bedrock has a tiny, almost imperceptible crack at the very extremes of energy? This is the radical escape hatch known as Lorentz invariance violation. The idea is not that Einstein was wrong, but that his perfect, smooth equations might gain a subtle graininess when dealing with particles of unimaginable power. Think of spacetime not as a perfectly flat sheet of glass, but as a sheet of glass viewed under a magnifying lens, revealing a faint quantum texture. At normal energies, a particle slides over this texture without noticing. But at the insane energies of our 50 cosmic rays, that particle might start to feel the grain. Its interactions with the sea of cosmic microwave background photons could change. Perhaps it becomes slightly more transparent to them, or the pair production process that saps its energy becomes less efficient. In this altered reality, the Greisen-Zatsepin-Kuzmin limit softens or even vanishes entirely. A proton could travel across billions of light years, keeping its impossible energy intact because the very rules of its journey have been rewritten at the quantum level. This brings us to cosmic ray 40, one of the most extreme events in the catalogue. Its energy was so far beyond the theoretical cutoff that it felt less like a particle and more like a mathematical impossibility. For the scientists analyzing its data, Lorentz invariance violation became a necessary ghost to consider. This single cosmic bullet could be the first empirical hint that our understanding of spacetime itself is incomplete at these frontiers. It is a notion that thrills and terrifies physicists in equal measure. The thrill is the potential for a revolution, a chance to peer beyond Einstein and glimpse the quantum structure of reality. The terror is the profound upheaval it would cause. Our entire framework of particle physics and cosmology is built upon Lorentz invariance being exact. If it falters even by a minuscule amount at these energies, it would send shockwaves through every theory we have, from the Big Bang to the behavior of black holes. Cosmic ray 40 thus becomes more than a mystery. It becomes a potential key to a deeper layer of the universe. It forces us to ask whether we are not just hunting for hidden cosmic accelerators, but are instead staring at the first experimental data for a theory of quantum gravity, a sign that spacetime itself has a limit we are only now beginning to touch. The solution may not be a new theory, but a new kind of eye. While our current giants like the Pierre Auger Observatory have mapped the broad landscape of the impossible, they are now being upgraded to see the fine print. This is the Auger Prime project, a sweeping enhancement that turns the entire 3,000 square kilometer array into a more discerning instrument. Its mission is to solve the composition conundrum once and for all, and it has a specific target in its sights, cosmic ray 41. This was an event that arrived with a shower profile stuck in the maddening middle, its atmospheric cascade whispering it could be a proton or it could be iron. Auger Prime is designed to hear that whisper clearly. By adding a new, thin plastic scintillator on top of each of its 1,600 water tanks, the array gains a second, independent way to sense the shower. The water tank captures the electromagnetic component of the cascade, while the scintillator is exquisitely sensitive to the muons, heavy electron-like particles that penetrate deep into the atmosphere. The ratio of these two components is a brilliant fingerprint. A proton shower produces relatively fewer muons. An iron nucleus shower, being a dense cluster of nucleons, creates a muon-rich cascade. For cosmic ray 41 and every ambiguous event like it, Augur Prime will deliver a definitive answer. Was it a lightweight proton whose path is a reliable clue? Or was it a heavy nucleus, a cosmic cannonball whose trajectory is a tangled lie? This single piece of data will cut the mystery in half, telling future searchers exactly where and how to look for the source. Beyond the enhancements in Argentina, an even more ambitious ear is being designed to listen to the sky's quietest static. The proposed giant radio array for neutrino detection, or GRAND, aims to do something no observatory has done before. It plans to use hundreds of thousands of simple radio antennas scattered across mountain ranges and remote deserts to listen for the ultra-high energy neutrinos and cosmic rays that current arrays might miss. Its strategy is one of sheer, overwhelming scale. Where Augur covers 3,000 square kilometers, GRAND envisions a network ultimately spanning 200,000. This vast, cheap array is built to catch the rarest of the rare, the cosmic rays with energies so high they might fall only once per century on a smaller detector. For an event like Cosmic Ray 41, GRAND represents a different kind of hope. Its radio ears are not just broad, they are exquisitely precise. By capturing the detailed radio pulse of a cosmic ray shower, GRAND could potentially reconstruct the entire three-dimensional cascade with a resolution that reveals something we have never seen before, the time structure of the very first interaction. It could answer whether the shower developed in a single, smooth surge, or if it had a jagged, multi-core beginning that hints at a heavier, more complex primary particle or even an exotic one. GRAND would not just tell us what the bullet was made of, it might show us a slow-motion replay of its moment of impact with our atmosphere, a forensic detail that could finally distinguish between a proton, an iron nucleus, or something entirely unexpected. These future detectors are not just bigger versions of the past. They are smarter, more specialized tools built to interrogate specific, lingering questions written in the data of our 50 mysteries. For Cosmic Ray 41, the question is painfully simple, yet it has blocked our path for decades. What are you? The answer will arrive not as a philosophical revelation, but as a clean, crisp data point from a scintillator or a radio waveform. And with that answer, the map of the cosmos will either snap into sharper focus, or it will tear itself apart, forcing us to acknowledge that the bullets we have been trying to trace are wearing disguises we are only now learning how to see. History offers a quiet reassurance in the face of such profound confusion. The story of ultra-high energy cosmic rays is not the first time the universe has presented science with an invisible, impossible reign. In the late 19th century, physicists were baffled by a similar ghost. They found that carefully sealed photographic plates in a dark drawer would become mysteriously fogged, as if exposed by a light that did not exist. This phenomenon was given a tentative, descriptive name, radioactivity. For years, it was a pure mystery, a defiance of known physics with no clear source or mechanism. The brilliant minds of the day, from Henry Becquerel to Marie Curie, did not dismiss it as a glitch. They recognized it for what it was, a crack in the foundation of their understanding. They widened that crack with relentless experimentation, and through it, they glimpsed an entirely new realm of atomic physics, discovering new elements and forces that reshaped our world. The cosmic rays we take for granted today had their own moment of baffling birth. In the early 1900s, scientists using electroscopes noticed that these instruments would slowly discharge even in a perfect vacuum. Something was ionizing the air, and it was coming not from the ground but from above. They called them quite literally cosmic rays, but for decades their origin and nature were fiercely debated. Were they gamma rays from space? Were they charged particles? The debate was intense because the data defied simple categorization. That defiance drove the creation of new detectors, high-altitude balloon flights, and ultimately the birth of the entire field of particle astrophysics. Each of our 50 ultra-high energy events is a direct descendant of those early, fogged photographic plates and mysteriously discharging instruments. They are not anomalies to be explained away. They are the next set of cracks appearing in a much larger edifice. Cosmic Ray 42, with its own unique signature of defiance, is not an endpoint. It is a beginning. It and every one of its 49 siblings represents a potential point of fracture in our current models of particle acceleration, intergalactic magnetism, and perhaps even the fundamental symmetries of space-time. The historical precedent is clear. When the universe hands you a particle that should not exist, you are not holding a problem, you are holding a key. The mystery of the 50 is not a sign of scientific failure, but a signal of imminent discovery, a gathering pressure that has always, in the past, heralded a revolution in how we see everything. To grasp the raw violence of Cosmic Ray 43, we need to translate its energy into human terms. The number itself is abstract, a measurement of about 200 exaelectron volts. So let us rebuild that abstraction from the ground up. Start with the most powerful machine humanity has ever built, the Large Hadron Collider. In its 17-mile ring beneath the Swiss-French countryside, protons are whipped to a staggering 99.9999991% of light speed. Their collision energy reaches 13 tera-electron volts. That is 13 trillion electron volts. Now take the energy of Cosmic Ray 43. It is not 13 trillion, it is 200 quintillion. To match the energy of this single natural particle, you would need to collide over 15 million beams from the Large Hadron Collider all at once in a single point. Our greatest technological achievement is a firecracker next to a supernova. Scale it up to something more visceral. The atomic bomb dropped on Hiroshima released an energy equivalent to about 15 kilotons of TNT, a fireball that leveled a city. The energy packed into Cosmic Ray 43 is minuscule by comparison, about 15 million times less than that bomb's total yield. But here is the twist: that bomb's energy was spread across kilometers of air, buildings, and Earth. The energy of this cosmic ray was concentrated into a single subatomic particle, a speck over 1,000,000 billion times smaller than a grain of sand. It is the difference between the warmth of a sunlit meadow and the searing, pinpoint heat of a welding torch held against your skin. The density of the violence is what defies comprehension. Perhaps the most humbling comparison is to the living world. A common housefly buzzing lazily through a room has a kinetic energy of about 1 microjoule as it flies. That tiny life force is still about 100,000 times greater than the energy carried by Cosmic Ray 43, so in absolute terms the fly wins. But once again, density is everything. The fly's energy is spread across its entire body, its wings, its muscles, its compound eyes. The cosmic ray's energy is crammed into a volume 1 billion times smaller. If you could somehow compress the entire kinetic punch of that housefly into a single proton, you would not just have a cosmic ray, you would have a particle that shatters every detector ever conceived. Nature is not just more powerful than our machines, it is more precise, focusing energies beyond our dreams into packages smaller than we can truly picture. This is the awe of the energy scale. We are not just witnessing a larger number, we are witnessing a different category of event. Our particle accelerators are like skilled archers, carefully drawing a bow to fire an arrow with immense focus. The universe, in creating Cosmic Ray 43, is a force that can take that same arrow and accelerate it to a speed where it ignites the air from friction alone, not by drawing a bow, but by tapping into fundamental forces we have not yet learned to harness. We are not building the gun, We are merely standing in the distant field, feeling the wind of the bullet as it passes, and trying to guess the shape of the shooter from the sound of the shot. Every one of these 50 cosmic rays is a testament to an engineering project of cosmic proportions, running on a power source we have yet to name, operating in a factory we cannot see. And all we can do is collect the shrapnel that occasionally drifts our way, each fragment a message written in the language of pure, impossible energy. The most profound mysteries always invite the most fundamental doubt. Could these 50 cosmic bullets be nothing more than cosmic coincidences, statistical ghosts in the machine? This is the fluke argument, a necessary and healthy skepticism that every researcher must confront. When you are dealing with events so rare and energies so extreme, the line between a discovery and a data glitch can be terrifyingly thin. The process of verifying one of these events is a fortress of statistics. It begins with the raw signal in the detector, a burst of light or a cascade of particle hits. Automated software first filters out the obvious noise, the constant rain of lower-energy cosmic rays, and the flicker of atmospheric phenomena. What remains are candidate events, and here the human and mathematical scrutiny intensifies. Scientists calculate the probability that the observed signal could be mimicked by a random confluence of background events, like several smaller showers accidentally overlapping in time and space. They run millions of Monte Carlo simulations, virtual universes of particle rain, to see how often such an imitation occurs purely by chance. For an event to be confirmed as an ultra-high-energy cosmic ray, that probability must be vanishingly small, typically less than 1 in 10 million. It then undergoes peer review, where other teams independently analyze the same data, checking for hidden biases in the atmospheric models, the detector calibration, or the statistical methods themselves. This process is designed to be merciless, to err on the side of dismissing a real event rather than accepting a false one. So, could one of our 50, perhaps cosmic ray 44 with its bizarre shower profile, be a fluke that slipped through? The rigorous answer is yes, it is possible. With enough data collected over decades, even a 1 in 10 million chance will eventually happen. The universe is vast, and so is the dataset. A single anomalous point, no matter how shocking, can never be fully trusted. This is why the second event after the "oh my god" particle was so critical, and why every subsequent detection has built a case not on individual brilliance but on collective weight. One impossible particle could be a mistake, 2 form a curious pattern, but 50, the odds that 50 separate events detected by multiple independent observatories using different techniques across half a century are all statistical mirages are not just small, they are absurd. You would have a better chance of correctly guessing the sequence of a shuffled deck of cards every second for the entire age of the universe. The fluke argument is essential because it forces us to prove the phenomenon is real. And the 50 have passed that test. They are not ghosts in the data, they are the data itself, a persistent, defiant signal written across the sky. The mystery is not whether they exist, but what their existence means for our place in a cosmos capable of such silent, pinpoint violence. The raw numbers behind these mysteries are not locked away in secret vaults. For the truly curious, the data for many of these 50 cosmic rays, including cosmic ray 45, sits waiting in public scientific archives, a digital treasure trove for anyone with an internet connection. You can visit the data portals of the Pierre Auger Observatory or the Telescope Array Collaboration and download the files yourself. What you will find is not a dramatic image, but a collection of deceptively simple numbers that hold the entire weight of the mystery. Each event is a row in a massive spreadsheet, a line of code that tells a story of a single catastrophic moment. There is the arrival time, recorded in universal time down to the microsecond, marking the exact instant our planet was struck. There are the direction angles, theta and phi, which translate to a precise coordinate on the celestial sphere, a point in the endless dark the particle seemed to come from. Next to that is the energy estimate, a number so large it is often written in scientific notation, a figure followed by a staggering string of zeros. And finally, there might be a shower profile, a list of numbers tracing the cascade's growth and decay in the atmosphere, like an electrocardiogram for a dying particle. This is the ghost made tangible. It is one thing to hear about an impossible particle, and another to see its fingerprint reduced to a set of coordinates and a power rating. You can take those direction angles and plug them into a free planetarium software, watching as a marker appears on the star map, hovering over that same empty patch of sky that has confounded astrophysicists for decades. You can compare the energy of cosmic ray 45 to the one before it, seeing the wild variance that suggests no single, simple engine is at work. This public data transforms the mystery from a distant, abstract concept into a concrete puzzle anyone can examine. It is a reminder that the frontier of human knowledge is not guarded by gates, but by the sheer challenge of interpretation. The numbers are clear, but their meaning is a void we are all peering into together, waiting for the pattern to finally emerge from the beautiful, terrifying noise. Progress in science is not always about finding the right answer. Sometimes it is about proving all the wrong ones wrong, one by one, until only the impossible remains. This is the art of exclusion, a meticulous process of elimination that has defined the investigation into many of our 50 cosmic bullets, including cosmic ray 46. Its arrival was recorded with precision, its energy placing it firmly among the elite impossible events. The immediate task was not to find its source, but to systematically eliminate every conceivable source we could imagine, watching as each promising lead withered under scrutiny. First on the list was the active galaxy. The particle's incoming direction pointed toward a region of sky containing a known blazar, a brilliant beacon powered by a supermassive black hole. It was a perfect suspect, a cosmic particle cannon potentially aimed right at us. The alignment was close but not perfect. More damning was the energy. Detailed models of particle acceleration in blazar jets have a theoretical maximum, a ceiling on how much punch they can deliver to a single proton. The energy of cosmic ray 46 soared well above that ceiling. Furthermore, if this blazar were the culprit, its brilliant jet should also be producing a cascade of ultra-high energy gamma rays, a telltale byproduct of such acceleration. Our gamma-ray telescope stared at that blazar and saw nothing out of the ordinary. The most obvious suspect was released for lack of evidence. Next, astronomers considered a starburst galaxy. Perhaps the particle was not born in a single, monstrous engine, but in the collective fury of 1,000 supernovae within a galactic firestorm. The general direction of the cosmic ray did align with a known starburst region. The appeal was its diffuse power, a galactic wind that could, in theory, accelerate particles over vast scales. Yet the models failed again. The turbulent shockwaves from overlapping supernovae, while powerful, are too messy and disordered. They can accelerate many particles to high energies, but they struggle to focus enough energy into a single, specific bullet to reach the extreme level of cosmic ray 46. It would be like trying to forge a surgical scalpel in a volcanic eruption. The raw power is there, but not the precision. The energy required pushed beyond what even the most violent stellar nurseries are believed capable of. Could it have been a transient cataclysm, like a neutron star merger or a rare supernova? The timing was checked against catalogs of gamma-ray bursts and gravitational wave events. Scientists searched for any recorded explosion in that part of the sky, from months to years before the cosmic rays detection, allowing for travel time. They found no match. More critically, the expected neutrino signature from such a violent, nearby event was completely absent. The ice cube detector at the South Pole heard no whisper from that direction. A transient event powerful enough to create this cosmic ray would have shouted its presence in neutrinos, yet the silence was absolute. even the exotic possibilities were put on trial. Was it a decaying super-heavy dark matter particle from our galaxy's halo? This would explain the lack of a visible source, as the decay could happen anywhere in the invisible cloud surrounding us. But this hypothesis predicts a specific pattern, an excess of such events coming from the direction of the galactic center, where the dark matter density is highest. The all-sky map of ultra-high energy events shows no such concentration. Cosmic ray 46 did not come from the galactic center. It came from a random patch of high galactic latitude, dealing a heavy blow to the dark matter decay scenario. One by one, the doors closed. The active galaxy, the starburst, the transient explosion, the dark matter ghost, each was examined, tested against the data, and found wanting. The evidence did not just fail to support them, it actively excluded them. This is not a failure of imagination. It is the rigorous, often frustrating work of frontier science. With each exclusion, the space of possible answers shrinks, and the remaining void grows more profound. For Cosmic Ray 46, the process of elimination left nothing behind but the empty sky it came from, and the chilling, exhilarating realization that the true explanation lies outside our current catalog of cosmic violence. The mystery deepens not because we have no ideas, but because we have run out of good ones and are now left staring into the dark, waiting for a new kind of light to dawn. The most profound puzzles refuse to stay within neat academic boundaries. Cosmic Ray 47 arrived not just as another data point, but as a perfect storm of contradictions that forced a council of experts to gather around its digital remains. Its energy was immense but not record-breaking. Its arrival direction pointed to another quiet void. The true puzzle lay in the cascade it left behind, a shower profile with a subtle anomaly in its muon content that refused to fit any single simple model. This one event became a nexus, a point where the separate languages of different sciences had to converge to even begin asking the right questions. The particle physicist looked at the muon excess and saw a challenge to the standard model of particle interactions at energies far beyond any earthly collider. Could a new, unknown particle be mediating the collision, or were the rules for how protons shatter in the atmosphere different at these extreme scales? They ran simulations, tweaking quantum parameters that had been settled for decades, searching for a combination that would spit out the exact number of muons the detector recorded. Their work was not about stars or galaxies. It was about the fundamental rules of demolition at nearly the speed of light. Meanwhile, the astrophysicist took the same muon puzzle and saw a clue to composition. That excess could mean the primary particle was not a proton, but a heavier nucleus like carbon or oxygen. This changed the entire search for a source because a heavy nucleus would be bent into a pretzel by galactic magnetic fields. They began modeling the Milky Way's magnetic field in finer detail than ever before, collaborating with plasma physicists who specialize in the behavior of magnetized gases on cosmic scales. These experts, who often study solar flares or fusion reactor designs, brought their understanding of turbulence and magnetic reconnection to map the invisible winds that could scatter a heavy nucleus across the sky. Their complex fluid equations helped trace not one path, but a fan of a million possible paths Cosmic Ray 47 might have taken, each leading to a different potential birthplace in the local universe. And watching over this entire collaboration was the cosmologist, who saw the event's very existence as a probe of the universe's structure. If the particle was a proton and survived from a great distance, it placed hard limits on the density and clumpiness of the cosmic microwave background, that fossil radiation from the Big Bang. If it was heavy and from nearby, it hinted at a population of hidden accelerators in our galactic neighborhood, forcing a rethink of how energy is distributed in the cosmic web. Cosmic Ray 47 did not yield its secrets, but it accomplished something just as vital. It proved that this mystery is too vast for any one field to solve alone. The particle physicist's equations, the astrophysicist's maps, the plasma physicist's simulations, and the cosmologist's grand models are all pieces of a single, sprawling intellectual engine. We are no longer just hunting for a cosmic gun. We are slowly, painstakingly assembling a new kind of lens forged from every discipline we have, just to catch a glimpse of what that gun might look like. The sheer scale of this mystery forces a question far beyond physics. Cosmic Ray 48, like all its siblings, is a philosophical object. It is a piece of a distant cataclysm, a splinter from an explosion or a rupture we cannot see, that has traveled across an ocean of time and space so vast our minds can barely hold it. And its entire journey, its million-year saga of magnetic deflection and near-light-speed travel, ends here with a faint blue flash in a tank of water on a quiet plain in Argentina. This is the staggering paradox at the heart of the 50. They are messengers from the absolute extremes of cosmic violence, carrying energies that dwarf our greatest machines, and we catch them with technology whose basic principle is little more than watching water glow in the dark. It is a testament not to our sophistication but to our profound connection. The universe is not a separate, distant painting we admire through a telescope's lens. It is an active, violent participant in our reality, physically reaching out and touching our atmosphere with bullets of pure energy. We are embedded in this cosmic storm, and these 50 events are the rare moments we become aware of the rain. They humble us because each one is a stark lesson in the limits of our comprehension. For centuries, we have mapped the heavens by the light they emit, building catalogs of stars and galaxies we can see. But Cosmic Ray 48 and its kin are emissaries from the dark side of that cosmos, from processes that do not advertise themselves with brilliant light, from engines that operate in silence or in wavelengths we are blind to. They tell us that our map, for all its beauty and detail, is drawn primarily in the visible spectrum, and that the true universe is shouting at us in a language we have only just begun to hear. This is not a cause for despair, but for a quiet, profound awe. Our place in the universe is not that of a passive observer in a quiet room. We are listeners in a vast, echoing hall, where every so often a note is played on an instrument of unimaginable power, and the single, pure tone travels across the hall to ring against our own small, waiting ear. The mystery of the 50 is not just a scientific challenge, it is a reminder. We are part of this cosmos, and it is actively, violently, beautifully communicating with us, one impossible particle at a time. The catalogue of 50 is not a closed book on a shelf. It is a living document, a ledger of cosmic defiance that grows with every passing year. As we speak, the silent giants in Argentina and Utah continue their watch, their electronic eyes scanning the dark for the next impossible flash. Cosmic Ray 49 could be the next line in that ledger, an event being processed right now in a data center, its numbers waiting to tell a story we are not yet ready to understand. This is the humbling reality of the frontier. The list is never finished. Some of the events we have journeyed through today, the ones pointing to voids or whispering of heavy nuclei, might one day find an explanation. A new telescope could peer deeper into that empty patch of sky and find a hidden galaxy. A refined model of galactic magnetism might finally untangle a scrambled path, pointing a steady finger at a known blazar after all. A single, brilliant insight could turn a baffling anomaly into a textbook example, but that moment of clarity will not be the end. It will simply make room. For every mystery solved, the detectors will have logged a dozen new ones, events with even stranger profiles, energies pushing even further beyond the limits, arriving from directions that make our current voids look crowded. Solving one piece of this puzzle does not complete the picture. It just reveals how much larger and more complex the full image truly is. The frontier of the unknown is not a distant line we are slowly approaching. It is a horizon that moves with us, receding with every step of discovery, always revealing new territories of awe and confusion. Our 50 cosmic bullets are not relics of a solved past. They are the first messages from a conversation that has only just begun. The latest entry in the ledger arrived in the data streams of the telescope array just last year. This is cosmic ray 50, a particle with an energy cresting 240 exaelectron volts, making it one of the most powerful ever recorded. Its detection was a quiet event in a Utah control room, but its implications are another thunderclap in the ongoing storm of questions. The initial analysis revealed its arrival direction with the array's now customary precision, and once again, the coordinates led to a profound celestial quiet. The particle seemed to originate from a region astronomers call the local void, an expanse of space near our own galactic neighborhood that is notoriously, almost unnervingly, empty of major galaxies. This is not the distant, deep void of earlier mysteries, but a relative emptiness close to home, a cosmic desert on our own intergalactic block. The fact that such an impossibly energetic bullet could emerge from a place we have long considered a barren backwater forces a brutal reassessment. Have we profoundly misunderstood the structure of these nearby voids? Could they be threaded with faint, unseen filaments of dark matter or turbulent magnetic fields that act as hidden accelerators? Or does this particle's path represent the ultimate in magnetic scrambling, a journey so twisted that its true source is a brilliant object lying completely outside the void, its signal bent by 90 degrees or more before reaching us? The shower profile added another layer of intrigue, suggesting a composition that was neither a clear-cut proton nor a definitive ion nucleus, but something ambiguously in between, perhaps a light nucleus like helium or carbon. This murky identity makes tracing its origin even more of a nightmare, as theorists must now run simulations for a dozen different particle types, each yielding a different fan of possible birthplaces across the local cosmos. Cosmic ray 50 is not a relic from decades ago. It is a fresh wound in our understanding, a data point so new that the papers analyzing it are still being debated in conferences and online forums. Its very existence is a statement that the universe's capacity for surprise is undiminished. Every time we build a better detector, every time we refine our models, the cosmos responds by firing another bullet that slips through the cracks in our knowledge, landing in a place we least expect. This is the ongoing discovery, the story being written in real time on servers in Utah and Argentina and Japan. The ledger of 50 is open, and the next line is being composed right now in the dark by forces we have yet to name. So we have walked alongside 50 cosmic enigmas, each one a silent bullet fired from the dark. We have traced their impossible energies that make our greatest machines seem like toys. We have followed their paths back to empty voids and quiet skies, finding no gun, no cosmic marksman to take the blame. We have questioned their very nature, wondering if they are simple protons or complex nuclei, a distinction that changes the entire map of their origin. And we have stood at the edge of known physics, where the only explanations left are whispers of dark matter decays, cracks in space-time, or laws of nature we have not yet written. This is not a story with an ending. It is a portrait of a frontier, a living testament to a universe that remains gloriously, defiantly mysterious. Thank you for exploring this ragged edge of human knowledge with me, for peering into the void where our understanding meets the impossible. The next time you look up at the night sky, remember this: that darkness is not empty. It is a sea, a turbulent ocean crossed by invisible messengers of unimaginable power. Every second, a silent rain falls, and very, very rarely, a single drop carries the echo of a cataclysm we cannot see. The mystery is ongoing, written in particles of light and shadow, waiting for the next curious mind to listen. Tell me in the comments which of these 50 cosmic ghosts captured your imagination the most. And if you want to join the hunt for the next great space puzzle, be sure to subscribe. Our map of the cosmos is still being drawn, and the next impossible clue could arrive at any moment.